Alright, time for another draftphysics.com, debatephysics.com, also video presentation, I think. I don't see it yet, but I'm probably here. Anyway, so, feel kind of crappy, so I'll make a video. Anyway, so there's this Jason guy, math and science channel. Nice enough fella, but it's too bad we can't get him to interact on any of these subjects. He won't in any way engage in any conversation about the truth versus what people claim to be the truth and whether they really have evidence for any of this stuff they claim. So he's going to be talking about microwaves, and he just says so many things about photons that I just think it's worth arguing that you don't have to believe this crap they tell you, okay, about what it is that a photon is, and such. So I figured it's worth playing, and so I figured I'd do a response video, and might as well do it live, and see if anybody has anything interesting to interject on the subject and such. So that's what we're doing. I'll hit the button.
On the counter is doing something, honestly, we take it for granted, but it's pretty incredible because by pressing a button, it's using invisible waves of energy that you really can't.
All right, so invisible waves of energy. Waves in what? Waves how? What are you talking about? Like laser beam waves? Come on, isn't that cat out of the bag? I mean, as soon as they make a laser, I mean, it just makes it kind of obvious that this idea of all of this stuff moving in all kinds of funky directions is kind of just nonsense, and you really have to see it as a stream of particles, and it's really not, I mean, it's not that foreign, it's not that alien a concept. I just don't know why it's so alien to these people that you could imagine that the frequency of a photon would, I knew that was going to happen. Well, I didn't know it, I knew it kind of. That you could just understand that the frequency is just, the distance between bits of stuff, and it makes it make so much more sense. This would be blue light, this would be red light. Now, there's polarization, what makes it a little complicated, but it's really not that hard to imagine that these things could be on parallel lines, and, that creates the polarization. And it's really about how they hit the surface that really decides when you make a photon, because a photon is basically creating electricity, and electricity happens in an atomic structure. It doesn't happen in a single atom. Where the hell did my mouse go? Yeah, there it is. Oh. Alright, so I clean my desk sort of, but there's still no room for a mouse anywhere. Anyway, so it's, you don't have to believe in these fields that are doing all of this crap, and just understand that the basic mechanism is just there's discrete bits of quanta, light quanta, as Einstein stated, and they're at a frequency, they're at a distance between each other at the speed of light, and it makes things like radio waves make so much more sense in understanding that there's not some wave that's going miles through space, between bits, that in fact it's just bits, and there's a bunch of them, and then there's less, and then there's a bunch, and then there's less, and then there's a bunch, and then there's less. But anyway, I'm just saying this model works so much better than this abstract wave notion.
But it must be there because they're using that energy to excite the very molecules of your food and heat them up. But my question to you is, how exactly does it work? And more importantly, should we be concerned in any way at all about blasting our food with these invisible waves?
I do have it sped up, obviously.
So the main thrust of this is we want to talk about how microwaves actually heat up food. So I find it really fascinating. But I want to start here with a story that's equally fascinating. So in the 1940s, there was actually an engineer-scientist who was working for a government.
So it's not a very good story, actually. It's just another story of another capitalist bullshit, didn't give it to mankind kind of thing, patented it, blah, blah, blah.
contractor called Raytheon. And that company was doing lots of radar work for the government, right? Shooting waves out into the sky to check for airplanes and things like this. And he was working with a device that we're going to talk about a lot today called a magnetron. Magnetron honestly has a super cool name. It sounds, I think, really, really cool. And it actually generates microwaves. So at the time, they were generating.
So you have lots of names like that, synchrotron. I think the diode that creates the microwaves, which you can use for, I can't remember what it was called though, but yeah, they all have a name. And it's just basically some way of creating an amplifier for a certain frequency. So you create a space in which you're putting the photons and they can vibrate in that space, and the whole machine starts to vibrate at the right frequency, and so it causes everything that hits to start vibrating at that frequency. So it takes stuff that's got a lot of frequencies in it and makes it into one less broad frequency.
These microwaves to shoot them in the sky and look for airplanes, and he was testing that. Now, this person had a candy bar in his shirt pocket right here in the front, and so as standing in front of the magnetron, they had no idea that this thing actually, could cause harm. They were, using it for other purposes. But after doing the work there, he noticed that the candy bar in his shirt pocket was slightly melted. So, this guy was not your average Joe. He didn't just...
Yeah, well, you would think that would happen anyway from your body heat, but whatever, continuing.
Blow it off. He actually investigated that further, and he did several other tests. So after heating up his candy bar, he went and grabbed some popcorn kernels and did the same thing. Put them in front of the magnetron. After a little bit, the popcorn popped, as we do all the time with microwave popcorn. Testing it further, he actually took an egg, a raw egg, not cooked, and put it in front of there, and the story goes that the egg actually exploded.
So this is more story than you actually need. So yeah, you figured out it heats stuff up.
This was a pretty powerful magnetron, heated it up from the inside and caused it to explode. So this person went on to patent the microwave for cooking purposes, and actually they brought the first microwave to market in the late 1940s. This sucker was like 750 pounds and thousands of dollars. It wasn't exactly something you put on your countertop. And over the years, of course, they miniaturized it, and now we have these things everywhere. We kind of take it for granted. But what I really want to talk about today, I do want to talk about how the microwaves are generated inside of the chamber, because I think that's fascinating. But I also want to talk about how exactly does a microwave heat your food up? Why don't the radio waves coming from the radio stations all over the planet heat your food? Why doesn't other waves that are around all the time coming from deep space, why doesn't that heat the food?
Well, technically it could, to some extent, but it wouldn't be as good. It wouldn't do it as well, and all that kind of crap. So yes, this is all about the fact that water molecules are more susceptible, and they do this, because of the fact that they're like little magnets. They have a north and south. You can jiggle them. So some atoms that don't have a huge amount of polarity, they're not going to move much in a magnetic field. But if you can put a stronger magnet in the field and then vibrate the field, you can vibrate the atoms. Simple explanation.
What's so special about microwaves? So we're going to talk about that and understand how it heats the food. All right, now as we dive a little deeper to really understand how any of this stuff works, the first thing we actually need to do is to...
So he's got the silly drawing behind him. Now, first off, the drawing is sort of a fake because the electric field is like 1,000 times stronger than the magnetic field, maybe 1,000,000 times. So it's not even, the blue part is much smaller than the red part, blah, blah, blah. But the whole thing is just nonsense. What is all that? How is the universe creating all that? How does it, how's it, something's going this way. It's moving, the speed of light in a direction. And then you're saying it's doing all of this weird crap. How can it possibly be doing it? It doesn't have the information inside of it to do all that. And the external universe can't be doing it because there's zillions of them. So what, what is it's just such a bizarre, unintuitive, unsimple description of the reality, and it's just so unnecessary because all it is a frequency. And again, the simple argument is because of the frequency. Okay, you could understand that if I throw 3 baseballs at a stick very close together in time, I'm more likely to knock the stick over than if I give the stick time to rebalance. So it's a tipping point argument that this will knock more things over. It doesn't have more energy. It can just knock more things over because the energy is more compact. It's going to disrupt atoms better, is the simple point. It's not more energy, but the trick is that it usually takes energy to make this compression. You can't make the frequency tighter and tighter without using something's momentum to do it. All right, continuing.
Zoom out and look at the bigger picture. We need to look at the electromagnetic spectrum. It's got a fancy word.
All right, so I noticed this is backwards. So in one visual, they have the low frequencies at one end and the high frequencies the other. Then the next visual is going to be exactly backwards. It's just so, there ought to be some consistency there, because this is sort of an important concept of understanding that there's an infinitely long wavelength, in a sense it could be as big as the universe, and there's a theoretical infinitely short wavelength where you have two quanta as close as possible, touching each other.
But we're going to break it down so you understand what that means. So you probably are already familiar with visible light. That's what's coming from the sun, bouncing off of everything in the room, going into your eyes. It's what your eyes are sensitive to, right? You also probably have heard of radio waves. That's something you hear about, obviously radio. And you probably heard of X-rays because you go to the doctor. And you may have heard of gamma rays.
So again, they have this completely the opposite way. So before they had the high frequency at the left and the low frequency at the right, and now they've switched it. And again, drawing them as waves when you could just draw them as a period, as a frequency, as a dot, dot, dot versus a dot, dot, dot. And that would be, I think, doing people a favor, them understanding a frequency. And again, none of this they never show a quantity of this. So how much is one of these, swirly things worth the same as, one of these little lines here? Or is it by length? Is it by how many ups and downs? I mean, what's the definition of a photon? How many of these ups and downs do you need to have a photon? I mean, it's just nothing. It's just such a loose and sloppy, in my opinion, description of the mechanics.
Fan of comic books and the Incredible Hulk. Well, microwaves are a part of the same family. X-rays, radio waves, visible light, microwaves. They're waves of energy that sit between.
So you could argue that but they're created in subtly different ways, and some of that means that they hit a surface in a different way. So you could argue that the radio waves are just a whole bunch of stuff in a pattern, and that photons are a lot more narrow and discrete. You couldn't make a laser beam out of radio waves. It would sort of be the argument. Their polarization would be enormous. And they're not going to cause this, they're not going to create the effect in the same manner. Yeah, I guess, I'm just trying to think of whether it matters to get into that much detail. Because the radio waves are basically hitting the whole surface, with the compression, where, a photon is hitting a little tiny bit of a surface and creating electricity.
Radio waves and the infrared, which is another frequency of radiation, with the wavelength somewhere around 12 centimeters, about the length of one of your cell phones. So if
you could argue that the antenna polarization is a good example of, just showing you how narrow it is and how the antennas need to be in alignment with each other, because basically the electricity goes up and it starts a pulse here. It's moving before the last pulse finishes. So it's a compression that has a slant to it, and it's the slant that hits the other antenna and pushes up the antenna. So the antenna is getting hit by something that's coming at it this way. So it's pushing essentially the electrons, pushing the electrons, pushing the electrons. So it's like taking a board in some water and pushing it at an angle. So the electricity, the speed of light of the electricity going up the antenna, almost the speed of light, you can understand that the first bit is ahead of the last bit moving. So it's not moving through space as a flat thing. It's moving through space at an angle, and that's the polarization. So a regular photon has the same polarization, in that the first bit is here, the second bit is here, the third bit is here. Okay, but it's a much smaller polarization. So the polarization ends up being something that can be variable on the surface. You can hit in any polarization and create electricity in a direction. Where in the case of the antenna has a a strict, narrow rule. I'm only going to see the energy that's in line with the antenna. You can't see polarizations in different directions.
Put your finger and your thumb apart, that's somewhere around 10 to 12 centimeters. That is what the wavelength of microwaves that were used.
Well, for some of us, it's a lot more.
In your microwave oven is. Now that wavelength of about 12 centimeters in your microwave oven, that's much, much longer than...
Okay, so we got the tight frequency at the left now and the loose frequency at the right. So exactly opposite again. I think obviously the sensible thing is to have the low frequencies on the left-hand side and the high frequencies on the right-hand side, indicating this tendency to get to places where it has more activity. Okay, the more compressed the photon is, the tighter these little dots are to each other, the more likely it's going to have a fracturing impact on an atom, because all the energy is positive energy. It's hitting it while it's hitting the electrons and hitting them while they're still moving. So there's no elastic rebound. You're not hitting against the force anymore. You're always just adding energy.
Visible light, which you see all the time, that has wavelengths less than 1,000th of a millimeter. Now, before we go any farther here, we need to talk a little bit about what wavelength actually is, right? It's easy.
Yeah, it'd be nice if they would say, okay, look, it's just a frequency. It's a period. That's what it is. Okay, you don't always have to think about this curvy, swirly shit, because it doesn't have anything to do with that. It's just a time interval between impacts. That's a frequency. That's a wavelength. Is that at the speed of light? Something moving the speed of light, the length will be the amount of time, and length will be related to each other. But it's just wrong to call it a wavelength. It's just a distance between bits.
Throw around terms, but you have to understand, or else you'll really not even know what we're talking about. So when we talk about the electromagnetic spectrum, you've probably heard of magnetic fields, right?
So this is all wrong. Nothing's actually doing any of this moving, because if it was, you could actually just take a magnet and make stuff move. So there's no stuff moving. Magnets are radiating just like radioactive material. The world hits them, and they reflect it different than what it hit. So the way it hit, the pattern of red and blue, let's say, in the field, hits it, and it filters it essentially. So it reflects what it's made out of, just like we reflect different colors. That's what the magnet's doing. One side's reflecting red, the other side's reflecting blue, so to speak. More blue, more red. It's never pure.
Have some permanent magnet, it's got a magnetic field around.
So again, it's just wrong. I mean, you just have to think of it in terms of it's just stuff radiating. Straight lines are all that's going in. Straight lines are all that's coming out of the magnet. And all of these field lines are just where they're sitting, drawing this very fake thing where there's an equal pull. So this is where they're just saying that the amount of attraction versus repulsion is equalized in this little line. But nothing travels that line. And the magnet doesn't make anything happen. The magnet's dead. It's just little arrangements of atoms. And they're polarized. They're all pointing in the same direction. So they all have their blue end sticking one way and their red end sticking the other way. Not all of them, but a substance of them. The strength of the magnet will tell you how many of them are aligned. The stronger the magnet and the smaller it is, the more efficient all of those alignments are. And but all it's doing is it's taking energy from the universe, just like we are, and reflecting it. And it's going to reflect with a pattern, and other magnets can see the pattern.
And you probably heard of electric fields. Those are the fields that surround any charged particle, like a proton or an electron. Anything that has a charge.
Right, so there's all this wooey stuff. There's no field. There's just the bits. There's just the photons, all moving, straight lines, going in all kinds of directions, all around everything. And there's just these simple interactions. What goes in comes back out. And it comes back out different than what it went in. And that's it. It's not any more complicated than that. The pattern's different. If it's hot, it increases the frequency. If it's cold, it decreases the frequency.
Has an electric field. Any magnet has what we call a magnetic field. Now, it was proven a long time ago that in classical theory...
Proven. None of this stuff was proven.
Talking about quantum mechanics here yet, but in classical theory, what we've proven is that light, the stuff that we see around us, is really a traveling wave, a disturbance in...
Okay, so it isn't any disturbance in anything. It's just nonsense. It's actual little bits, and the little bits are changed by everything they hit. Everything they hit, they reflect off of it, and different stuff bounces off than what went in. White light hits me, and it comes back as red over here, and blue and black over there, and some other color over here. Well, there's no black color, but so it's all about interactions and reflections, and there's no fields.
Electromagnetic field. So a disturbance in the magnetic field that's permeating space everywhere, and a disturbance in the electric field which is also permeating space everywhere.
So make up stuff. Yeah, okay, it says you. There's just no evidence of any of these fields and what they would be made out of. And there's ever pretty good evidence that what it's made out of is the stuff we're always interacting with. And when we're interacting with it, all we're doing is, again, changing it. We can't make more of it. We can't make more energy in the universe. We can only take the energy that comes in and we can do something to it and change how it comes out. And so for every color I don't absorb, I mean, it doesn't reflect, I have to absorb it. And then I have to admit it as some other kind of radiation. Infrared or some other color you can't see.
But it also goes a little deeper because we know from physics, from what's called Maxwell's equations that govern electricity.
So that Maxwell's equations basically do, draw the charges as straight line force. That's the inverse square law. It does work really well. And again, this Faraday notion that these field lines are the real mechanism. Those aren't real things. There's nothing traveling those lines. Those lines are completely arbitrary. I change how big the little particles are that you use to see those lines. Those lines get smaller and smaller. I can make those lines any size, and I can put them almost in any place depending on how I change the mass of the particles I'm using to see them. They're synthetic. They're not real lines.
The magnetism. We know that these electric fields and these magnetic fields are coupled together. And all that really means is...
So we know it. So again, it's just this little tiny, whatever it is, 0.002% of the human race who all went to this, got the same education, and they believe this religion, and they preach it to the world and tell us we have to believe in their Holy Ghost. And that's all this stuff is. This is just Holy Ghost theory. They really have no good evidence to say they've proven the existence of any of these features or properties. They haven't proven that these things have the properties they claim.
That when the magnetic field has a ripple in it or a change or a disturbance, that disturbance generates an electric field.
So all you're doing when you're disturbing it is I just move. I move it. I move the red sweater. I'm changing where the photons are going and what they're going to hit. That's all I have to do is move it. So I just move the atoms, and I move the object that's radiating these colors, and where you can see the colors will change. Places will see the color where they didn't see it before. That's all that happens. You're just changing how it looks. Everything's looking at everything else, okay, in the sense that then they're seeing it through these photons, and even though you can't see infrared, you can feel it on your skin, so you know it's there. You know there's all kinds of information hitting you, all kinds of stimulus hitting you, and you don't have to be, you don't have to sense it to know it's happening.
And we also know that separately, any change or disturbance of...
So look at that crap. I mean, this is all just made up wooey bullshit. Again, nothing does these curve paths are just synthetic drawings of where they say, well, where's the equal forces between, if I take a positive charge, what will it do if I put it into space and give it a velocity? What will it do? And that's all that is. But these aren't pathways that everything travels. There's no actual field doing that. It's just a way of saying, well, what's the relationship between the negative force and the positive force, and how do they affect something when you're closer to one and further from the other? It's just wrong to say those lines represent actual force lines. They're not, they're field lines. They're not force lines. The lines of force are radiating straight out of the object.
The electric field produces a magnetic field. So I always like to say that magnetic fields and electric fields are like peanut butter and jelly. They go together. When one of them changes...
So there's no two different fields. There's just the photons. And the fact is they are in two colors. There's electron force and proton force. And the fact is that if you're looking at something, you're seeing mostly the electrons. But the fact is you do see some protons. So you're seeing what's reflecting off of them. And you're seeing what the pattern looks like after it hits. You're taking purple light and throwing at a surface, and in some cases, if it's well polarized, you're going to see a definite separation between the blue beams and the red beams. But you hit something else and it just comes back purple. Something non-magnetic.
Causes the other one to arise. When the other one changes with time, then it causes the other one to arise. So if you have this rhythmic undulation in an electric and magnetic field, they
blah blah blah. So let's just say there's only a magnetic field. You guess you could argue, because charge is basically electrons and protons are the magnetic monopoles. But the field is just this. It's just photons. It's always just photons. It's all made out of the little bits and them reflecting and them having a pattern. And if you have the right condition, you can see the pattern. If you're a magnet, you can detect the difference between red and blue. If you're not a magnet, you can't tell the difference.
travel together as a wave through space. That's called an electromagnetic wave.
Yeah, so it's just bullshit. So it doesn't happen. And again, the drawing is a deception right on its face because the one field is whatever it is, 1,000,000 times or 1,000 times stronger than the other field.
Now, when you get deeper into physics, you learn that magnetic fields and electric fields are not really separate things. They're part of a larger...
Right, so you just told us one thing, and now you're going to tell us something else. So they're two different words, two different fields, two different blah, 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 and now you're going to say, no, not really. Yeah, so exactly. It's just such wooey, mushy bullshit.
Construct of one field called, you might have guessed it, the electromagnetic field. We see them as separate entities when we look at a magnet or a charged particle, but really the larger construct is that they're unified under one thing called an electromagnetic field.
Yeah, so you just put the two words together. So again, the very fact is that it's substantially about electrons, because electrons on the outside of all atoms, so the electro part is correct, okay, but the fact is that it's just about polarization. So it's just about the elemental fact that you know, you can kind of, at least you should be able to understand that you know, an electron and a proton are, you know, if you put two of them right next to each other, you would have what's called a neutron, and you have, that's the smallest dipole. And the simple argument is that when you take the force, the mixed force, and throw it at these dipoles, they're going to reflect their character. So one's going to reflect all red, and the other one's going to reflect all, if it was blue, all blue. And so it's taking something that's mixed, and it's going to basically filter it for you. And that's what all those little neutrons inside of the atoms are going to do. And all of the arrangements, you know, you can take that neutron and create deuterons and, you know, make them bigger and bigger arrangements of electron, proton, and those arrangements are going to send this difference is going to be visible. And the photons that made it visible didn't have the pattern in them. The white light didn't have a pattern. Now the white light has a pattern. When it reflects off of me, you can see a pattern. All kinds of different colors. Well, that's what happens every time you throw light at an atom, is that it's going to come back different than what you put in. what parts reflect and what parts absorb are going to change the pattern.
But for the purpose of this discussion, what I want you to know is that any of these things that I've talked about, whether it's microwaves, whether it's visible light, whether...
So we're back to the gamma rays being at the left and the slow-moving radio waves being at the right, which is, in my opinion, just so unintuitive. It's just completely reversed. Why would you put the fast thing in the beginning, the high energy thing, so to speak, at the beginning, and the low energy at the other end? It just seems so backwards.
It's infrared waves, whether it's gamma rays, whether it's X-rays, or any other word that you can you've come across dealing with electromagnetic radiation. They're all the same thing. The only difference is the wavelength and frequency are different between those different ranges.
Right. So there are differences. Like I said, the light is being created by a small section of atoms. Okay, the photons, and they're in all kinds of arrangement, create all kinds of polarizations, and the antenna is just creating essentially one polarization. So you can't pick it up. You can't pick up any antenna energy at the wrong polarization.
You have visible light, which is pretty short wavelength. Then you have this microwave stuff, 12 centimeters. That means how long does it take to wave? And by the way, what's waving? The electric and magnetic field.
All right, so what's waving? What's the magical stuff is, just sorry. It's just so... They don't have any hard evidence that any of that crap is true. It's just that, like I said, they just believe it. They just talk about it like they drew a picture on the top of the Sistine Chapel of the Holy Ghost or something, and therefore we have to believe the Holy Ghost. But the polarization is real, and that's what he's basically talking about. The distance between the frequency tends to be proportional to the polarization, that is, the distance apart at the speed of light. This is the speed of light going this way, but when you put it through a substance, when you put the electricity into something to create these photons, and you're not creating them, you're remaking them. You're taking a surface and you're taking your electrons on your surface and you're doing this with them. And when you do that with an electron, it's going to compress the field that's hitting it. So all the photons that are hitting my hand, if you can understand my hand could go half the speed of light or something, you could sort of recognize that what did my hand just do to the universe? Well, all the light that hit it, it just changed the frequency. It just increased it by half. It just turned red into blue light. And the opposite was happening on the other side. There's, my hand was becoming invisible. So when my hand goes away, if I could make it go fast enough, it's almost like it wouldn't exist. And it's going to take all of the visible radiation and make it so long that you're not going to see it anymore. Nothing's going to reflect if I go fast enough. And but that's what's really happening. The surface isn't shooting out little bits of energy. It's pushing out electrons. And when the electrons push out, that's like my physical body pushing out, and it's just going to sit there. Like I said, if you throw little bits at me, paint, and the paint has this kind of distance between the little particles of paint, and they're going to reflect off my hand, well, you can understand I'm going to compress them by pushing. They're going to reflect with a much smaller frequency, and that's what's really happening. All right, we do have a comment. Let's see. Because the further it moves, the less powerful they are. So the waves are correct in that picture. That wasn't what I was talking about, you retard. I'm talking about putting the tight ones at this side, and then the next image putting the big waves at this side. I'm saying it's not doing obviously these videos are made for morons. So, I mean, if you're going to be teaching morons, you shouldn't keep switching the diagram left to right, moron. You just explained exactly what waves are saying in the picture, LOL. Fuck you, I did. You just go fuck off, you jackass. You're so fucking off the subject. Twisted star. Fuck it. Goddamn star for brain. Ugh. People are just, you are so stupid. You're such a fucking dumb, ignorant dupe. Ugh, it's so fucking irritating. I have to be on a planet of complete ignorant moron. Ugh.
The distance in space when one of those quantities begins to repeat. You remember a sine wave, right? So it goes up as a sine wave.
Yeah, it goes up as a sine. All that crap is just that crap. There's just no evidence of sine waves, that photons get stronger and weaker, and all this. None of that shit happens. It's just absolute bullshit. They're bullets. They're bits of energy. That's what Einstein kind of proved, along with Planck.
Back to its starting point. Visible light has a very short wavelength. It wiggles very rapidly. Microwaves have a relatively long wavelength, but certainly there are lots and lots of...
So, and all of these lengths are all relative to our perspective. So, you could call us, you can say we're in a very, very hot environment. You could say we're very, very cold compared to the sun. So, it's just playing games, with the fact is the little spectrum we're involved in just happens to be at a critical difference in terms of what atoms can do. And, atoms are really just converting infrared into visible. And it's hard for them to do ultraviolet. It's not an easy thing to do. So we know that all of the radiation in the high spectrum is very rare radiation compared to the radiation in the lower spectrum. There's a ton of radio and a ton of microwaves and a ton of all of that shit in the universe. The infrared especially, huge amount.
Frequencies longer than that. The radio waves in the AM band that you maybe listen to on AM radio have wavelengths that are very, very long. They can even be meters and meters long and kilometers long. And then you can have...
Yeah, exactly. Kilometers long of some silly snaky thing. Do you really believe that? Miles of snaky thing, and it hits the surface, and the surface can detect the snakiness of the mile-long snaky thing. It's a ridiculous theory.
Very, very short wavelengths, even shorter than visible light, like gamma rays. So basically what I'm trying to say is they're all the same thing. We have different names for them, but the only thing different is the way...
Right, so look, we know this about photons, is that, yes, they have this consistency. So it moves this perfectly, always the same speed. And the simple truth is that you can just change the frequency. And so, and the change is just as obvious as me saying I could change the frequency just by pushing an electron into the photon energy. And I'm automatically, whatever stuff is going to hit me, whether you believe in waves or you believe in particles, whatever stuff is going to hit that electron, the absolute fact is it's now reflecting much sooner than it would have. So therefore, it's going to compress. It's going to be much more compressed in the field when it leaves. So you can understand if a radio antenna is pushing hard, okay, all the electrons are pushing out because you're compressing the atoms and pushing electrons out the surface, that you have this huge amount of pushing happening, and that everything that hits is basically getting compressed. And then you have that little compression moment, and then the electrons are swung in exactly the opposite direction. And so now you have a whole bunch of space where there's no compression, where nothing's reflecting very much. And then again, you're going to push them out and compress them again. And so that's what you're creating in the space, is you're creating this blob of density, a whole bunch of quanta, not so much, a whole bunch of quanta, not so much, a whole bunch of quanta. That's what you're doing.
Wavelength is getting shorter and shorter and shorter, and we call them different things. And the frequency is related to the wavelength, and so it changes as well.
So this is the point, moron. You see how the other image had the little tiny tight things over here and the big things over here. I'm just arguing that it's not very intuitive to keep switching the model from left to right to left. It's like if I did that with text and I turned the sentences right to left and then left to right and then left to right, it's not going to be a very good learning tool.
We have different names, but it's all the same phenomenon.
This is the bariatric gelatin bedtime recipe that took
Oh,
me from
poo. I
198
have
to
to go find the
147 in
video to
just
turn
weeks.
that off.
It's natural, simple, has zero side
shit.
effects, and takes less than a minute to make. No
That's not it.
$2,000 injections needed. Just one glass of this gelatin trick before bed.
Oh, fuck
and
you.
I'm pretty sure
Fuck
you already have
Fuck
everything
you.
you
Shut up.
need in your...
Fuck you, bitch.
Now here is where I think it
Dumb
gets
cunt.
actually interesting and where I want to spend a lot of my time talking to you today. These waves, these 12-centimeter waves in the microwave region, they were chosen very specifically to heat your food. And why? Because they have an ability to interact with...
All right, so obviously they weren't chosen; they were discovered. Okay, so again, so he already told the story that the guy found it by accident, and I'm sure they just said, "Oh, gee, we can't do it with lower frequency, and it won't work with a higher frequency." So yeah, this is the frequency, but it's not like they discovered it.
Something you might not be thinking about or expecting in this talk. They interact with water molecules very efficiently, and your food is absolutely packed with water molecules. First of all, most people don't actually know that if you put something in the microwave that has no water content in it at all, like, and I'm talking about no water, it won't heat up in a microwave oven, right? Even things that you think are pretty dry, like some old stale bread, there's still some water molecules in there. Even a brick, if you go grab a brick from the backyard, it's pretty dry, but there's water in there. There's water vapor, it seeps into the pores, it's in there. So even a...
So we do know that it will conduct, some little pieces of metal will conduct the electricity to convert the microwaves into electricity. So you can, create other mechanisms to generate heat. So it's not just water. It will affect other compounds. It's just you got to pick a compound that has a certain amount of iron in it or some other material that will also collect microwaves. Collect them for a different reason, but it collects them. I mean, the little iron filings will collect the microwaves, but it's not collecting them because of a jiggle. It's collecting them because it's creating electricity.
brick will probably heat up. Even a ceramic plate will heat up in the microwave because there's a little bit of water in there. But if you literally put something in there that has zero water, it will not heat up.
A ceramic plate? Well, not a glazed one. You're not going to get any water into a glazed plate.
And the reason is because the frequency and the wavelength of the microwave radiation in your oven is very specifically chosen to...
All right, so it wasn't chosen, whatever. It was just a fact that they found, oh, that's the one that worked. Again, the fact that, yes, this is really a conversation about that relationship between the fact that water is one of these uniquely bipolar molecules. You know, it's very polarized.
agitate and heat up the water
It looks a lot like a magnet.
molecules. And when the water molecules get agitated and heat up, then of course they heat up the rest of the food and everything else in there if the water is mixed in throughout the food. Now to understand that, and that's what I mostly want to talk about today, I need to talk to you about something called resonance, because I'm going to show you how a water molecule is affected by this type of electromagnetic radiation.
So he does a pretty poor job of this. Okay, so this might be a big waste of time, but we're here, we're going to play it.
I'm going to talk about resonance. You've probably gone to a playground and pushed somebody on a swing. Right? So pretend this is a swing here, right here. You can make the swing short and you can make the swing long, right? There's different choices. But I want you to notice what happens. If the swing is long, notice that when I push it, it's ticking tock, tick tock, tick tock, tick tock, like that. Notice that
all you have to do is have a frequency, okay, that allows you to hit it when it's moving in the direction you're pushing in. So if you can do that more, then you hit it in the direction it's not going, that is the opposite direction. So it's coming at you and you hit it. So as long as your whacker has a frequency, a harmonic, or a frequency that is more often hitting it when it's going in the same direction and less often hitting it when it's going in the opposite direction, especially hitting it when it's at its peak velocity in the opposite direction. So if you can avoid doing that, then you can keep adding energy. And that's all you're doing. You're just adding energy. You're not opposing any of the energy. You're not counteracting any of it. So as long as you keep hitting it when it's moving in the direction that you're pushing, then you'll just keep adding energy. You'll make it go higher and higher and gain more and more velocity.
if I change the length of this pendulum, is what it's called, maybe a little bit shorter, and I push it, then it's going to do something like this. Tick tock, tick tock, tick tock, tick tock, tick tock. You see, it's vibrating, for lack of a better word, at a different rate or a different frequency just because I changed the length of it. We can see it one more time. Tick tock, tick tock, tick tock. And then when I make it long, tick tock, like this.
So there is something intrinsically a little creepy about that whole demonstration, but whatever. Tick-tocking.
Water molecule has a certain shape and a certain size, and it has
Real men don't tick-tock.
also what's called a resonant frequency. It likes to vibrate at. Just like this pendulum, it likes to vibrate in a certain way. You just saw it.
So it wasn't that it likes to, it's just that you obeyed the rule of putting more energy in the same direction than in the opposing direction. So as long as you keep putting more energy in the same direction, you'll be adding to its energy rather than subtracting from its energy.
Change the length of the pendulum, and the thing vibrates differently. The water molecule has a certain shape and a size, and it likes to vibrate in a certain way at a certain frequency just because of its shape and its size. All right, next part.
So I guess I'd say it's more about the fact of the whole structure of how water molecules stick to surfaces and how they stick to each other. And the fact is you're just breaking that structure. So you're automatically turning the water into, you're breaking it from liquid into gas. And the gas is automatically hot.
This thing I need to teach you about. If this is the pretend water molecule here, it likes to vibrate at a certain frequency. What happens if I want to put energy into this thing? I want to make it go higher and faster. You all know that when you push people on a swing, you have to push at the right rate. What you're doing is you're matching the frequency, the natural frequency of the oscillation.
So it's not the natural frequency or anything, it's just that the fact is it moves at a certain velocity and has a certain amount of elasticity, and you're just taking advantage of its elastic motion, how well it restores its condition. And so that's all about how strong the atomic bonds are, and all kinds of stuff will decide how much of that you can do.
The frequency of your pushing. Let me show you what I mean. We'll go longer here. Here we go. Push, 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 push.
So that's as bad as the tick-tocking.
Push. You see, I'm timing my pushes to be perfect, so that when the thing comes back, I'm ready to push again.
I know, but you're doing it when it comes back, so that's just so kind of obvious. So it'd be much more interesting if you were shooting a gun at it and you had to hit it when it was at the bottom of its arc, and you had to always keep hitting it when it was going in the right direction at the bottom of its arc. Be a better illustration.
The frequency of my hand to the frequency of the pendulum. But what if I'm pushing way, way too fast for the length of this thing? Here we go. Push, 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 push. That's hard to do. Push, 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 push. You see, I'm wasting a lot of energy between the pushes if I vibrate too fast. Well, what if I vibrate?
So it's just that you gave it too much velocity, so that's what happened there. So you broke the pendulum because you gave it too much velocity, and so it didn't swing, you shot it, in a new direction. So you made a mess out of it. But you're always hitting when it has no energy, when it's dead. So you can't possibly hit it at the end of its voyage and not be putting resident energy in, So again, he's just sort of got it wrong. You have to avoid hitting it when it's moving against you. So that means you have to be in a position to hit it when it's moving against you. And if you're already at the outside where it stops, where it's already lost all of its energy, then you can't possibly be hitting it against its motion. So it's better if you had your hand in the middle than way down here at the outside. Have it right at the middle, and understand you have to push then.
Too slow. Oh, I'm so slow, and I'm ready to push again, and I'm really,
so
really
look,
slow.
it's gaining energy, so he's not showing how it's failing. He's showing how that worked just fine. That slow frequency worked just fine. You let it swing a few times, and then you push it again, and then you let it swing a few times, and you push it in the right direction again. So it was a really poor demonstration. What you have to avoid is your hand hitting it when it's got a lot of velocity in the opposite direction, because that's the energy killer. It's when you hit it and destroy its progress. You force it to lose its momentum. It's about adding momentum. Oh, damn. All right, somebody else commented. Let's see if this was any better. It's theory upon theory upon theory. No, it's story upon story upon story. I wouldn't mind if these were sort of theories that were sort of rational and you could sort of dissect where they came from. But you can't even dissect where this mush comes from. All the way down, of course, through science, though science was supposed to be about evidence. Exactly. And it's about not jumping the evidence. Jumping the shark, jumping the evidence. Same thing. It's not doing good science when you jump the evidence, when your conclusion horses, are, when your conclusion cart is way ahead of your horses. It's just, this is completely open to conversation about the best interpretation of the evidence, and they closed that door, 200 years ago. Let's see, these assholes never made it past their CAD hypothesis. I don't know what that even means. I don't know what that means either. Let's see, the very first step in the scientific method. Yeah, well, I don't even much like the word hypothesis and theory and playing games with, the level of your description of a reality. I'm saying there's ways of describing things, and they're either accurate or inaccurate. They're either proven or unproven. And so that's the argument. If you're going to say photons are waving, well, you have to have some kind of hard evidence, okay? And I don't think they have that yet. And I'd argue that better interpretations of all of these experiments will show that particle models work better. So you could just say, a lot of this isn't a hypothesis, it's a model. You're saying, here's a model of a physical mechanism. This is how it works. So they have a model of an atom with these silly electrons flying all over the place. And it's a silly model, because it can't even work even if you understood charge and you understood that photons or electrons were somehow being controlled by charge. It still couldn't work, but you need to change the velocity too many times. It can't possibly be the right answer. And it makes so much more sense to say, obviously, when they say it's sharing an electron, it means it's literally sharing it. The electron's in a position, and the two nucleuses are in a position, and they're jiggling, but nothing's moving around. I mean, it's a silly model. So it really is just about modeling, and it's about how realistic the model is, how many flaws, how many, and again, and they're going to argue that somehow they have evidence when they say things like, well, we did a double slit experiment with electrons. And then you go research and you find out there was no double slit experiment. They shot electrons at a crystal. They didn't shoot it through slits. It's just all such bullshit. Well, of course, I can explain how a generator works, okay? I mean, you're still pushing magnets into magnets. That's how it works. It's not that complicated, all right? And the fact is yes, it's like just saying that just as you can induce magnetism with electricity, you can create electricity with a moving magnet. So that's all you're really saying, is you're trying to say that if I rotate a magnet in, especially in another field of magnetism, I'm going to cause electricity in that metal. So what? There's nothing magic about it, right? I mean, let's concede there's no free energy in generators. I can't spin the generator twice as fast and get 4 times the electricity, can I? So frankly, how are you going to use generators as being an argument against what photons and magnets are? Again, it's your theory that magnets have some kind of swirly stuff around them, that they're causing some sort of motion. How can they do that? What energy do they have? They don't have any energy. You have to understand, a magnet can't be creating something. It doesn't have nuclear forces. It's not it's not decaying. It's not, the atoms aren't falling apart and shooting their bits, releasing their bits. So how the fuck can you sit there and think about it as being some sort of machine that's actually doing something all the time? It's not doing anything. It's just reflecting the world that hits it. I'm just curious of your thoughts on it. Well, we'll get to that, okay? Because frankly, it's part of the story. But this subject right now is photons. Okay, I prefer to stay on the subject of photons. Yeah, no, I 100% agree. And yeah, to be scientific theory, there should still be some, preponderance of evidence pointing to the answer. They don't even have that. It's pathetic. Well, the fact is, and they won't allow the argument. I mean, it's all one-sided, right? There's just the prosecutor and there's no defense attorney. So it's so one-sided. So the prosecutor just says, well, here's a drawing of a gun. It looks like a gun that guy could carry, right? He could carry this. So let me put that on the evidence table. He had a gun. And there's no defense attorney to show up and say, well, that's not a gun. There's no defense attorney to show up and say, shooting electrons at a crystal is not a double slit experiment. It's just lying to call it that. Saying that time is a dimension is just babble, because there's only 3 possible dimensions, and you can't make a 4th one and have it follow the rules of a dimension. So there's no defense attorney to show up and say, you can't play these word games. What the hell's a scalar energy? How the fuck can something have a magnitude in no direction? How can you make something? How can you even draw magnitude with no direction? How exactly does that happen? But there's just no fair trial here. It's just this one-sided babble from these preachers, and nobody else is allowed to object. There's no judge for me to say, please, judge, he can't do that. That's not science. You can't just make up shit. Richard Feynman would have been thrown out of court if there was a real court. When he drew this sloppy diagram of the double slit experiment, just made up shit, and you're just like, what the fuck is this conversation? You can't even draw the pattern correctly. All right, back to the video.
Efficiently, because my hand wasn't ready with the next push if I go with it too low of a frequency mismatch. So if I don't match...
So you don't have to have the right frequency, you just have to have a harmonic that's going to do the same thing. So again, you could hit it once and then walk away for a minute and then come back and hit it again. So you could have all kinds of frequencies that will still add energy. Okay, but one of them will add it more reliably.
Frequency that's natural of this pendulum, either too slow or too fast, I don't couple the energy of my hand very well into this thing, right? But if I push it exactly right, and if I match the frequency as perfect as I can, then what you do is you enter something called resonance, and that means that I'm coupling the energy efficiently. It's the same thing. You see the opera singer, and they're trying to sing, and you see that the really, really talented ones can get the wine glass to break, because that wine glass...
Okay, we can't see that. So again, it's just an urban legend, right? There's just zero evidence of anybody ever doing that without some kind of some mechanical aid to amplify their voice. So, he's just talking, that's just such shit to talk. Like, oh yeah, we can see that. No, we can't see that. There's no such thing as the video of the opera singer breaking the glass. It just doesn't happen. But yes, the idea that we can see glasses vibrate when you hit them with sound frequencies, and you can watch the glass oscillating, and you can say, yeah, okay, I can see how if you can finally get it loud enough or intense enough that the glass will break. So yeah, that you can understand. And what else did he say? Well, anyway, let's continue. I'll think of what he said.
It's made up of molecules, there's elasticity, and they flex and they vibrate, and it has a natural frequency just like that pendulum. And if I match my voice to the correct frequency, I can get, just like the swing set, I can get you going very, very high if I do it in the right frequency. I can break that glass. And if it's too low or too...
So he keeps saying it, but no, it's more about how much you have to have a really loud sound and the right frequency. You have to do both. And you have to start it off wobbling, and then you have to increase the frequency until you get to a point where you can actually fracture it.
It won't be so good. All right, so now that you have that concept underway, or in your mind, fresh, of resonance, now we have to tie it back to the water molecule. So a water molecule has what we call a polar character to it. We actually call water a polar molecule. And that means that the water molecule actually has a positive end to that molecule. And also the other side is a negative end. So it's kind of a...
So it's really the opposite, okay? Because the hydrogen is just the electron and the proton. The electron is what it's sharing. So it's sharing its electron. So what is it showing the world? Well, it's showing the world its proton. So it's very positive. The hydrogen atoms become very positive looking. And the oxygen atom looks very negative because it has a whole bunch of extra electrons on it. 8 or 10 or whatever.
Charged molecule, one side positive, one side negative. Most molecules are not like that. Water is kind of special. That's why water is really so good at dissolving things, because it has charged ends to the molecules. So the oxygen atom, which is in the water molecule...
So again, yeah, this is how they describe it. I tend to say there's got to be something more to it, just because you would think it would be a little bit magnetic, and it doesn't seem. You can move it with charges, so it does move in a charged field. You can actually create electricity by moving water. So water will carry a charge, but real just plain magnets I don't think will move water. So that's the weird part. But again, that just has to do with, I guess, how the water molecules connect to each other. That they lose their polarization. You know, they're very polarized, but you can't line them all up in the same direction. I guess that's the problem. So individual atoms of water can collect charge on a surface, but all the water molecules themselves, you can't line them all up in the same way because they connect to each other in inverse. You know, instead of red, blue, red, blue, red, blue, they connect to each other blue, red, you know, and so it's all chaotic. So there's no capacity to make it magnetic water. But it has the polarity where you'd say, gee, that's an atom you could make a magnet out of. But you can't do it because you can't arrange them where they're all red end up and blue end down. I guess that's a better way to make the point.
Has extra electrons, it creates a negative charge at one end because oxygen is so good at pulling in the electrons. And hydrogen, which is also in the molecule, has a sort of a net positive charge at that end of the molecule because hydrogen just doesn't have enough nuclear charge in the center to pull the electrons effectively. So this polarity is crucial to how microwaves heat your food. Before we move on, I want to talk about that just a little bit more. Here's your friendly neighborhood water molecule. You have H2, that means 2 hydrogens, 1 oxygen. Now,
so I don't know why they do this either. They know the oxygen atom has got a lot more electrons and protons in it. And they know the hydrogens are pretty small, okay, just an electron and a proton. So why is everything the same size? I mean, that's kind of bullshit right there. So it does give you a very distorted view of, you know, what's going on. And obviously this gigantic separation, you're saying, what's this gigantic separation about? You know, there's no reason for it. It can't be separated because it's sharing that electron. The electron's got to be a lot closer to that atom. So anyway, it's just not a perfect diagram. All right, so anyway, Matt says, why do you think they do this? Control, question mark, keep everyone stupid, I guess. I don't know. I thought about that today. I'm just saying, of all these physics, you know, when they hear the physics, they're getting taught the physics, why don't they figure out that, well, you just told me it's a double slit experiment, but there's no slits. I mean, that's not a double slit experiment, right? Come on, let's not be fucking around here. You can't call it a double slit when there's no double slit, right? I mean, you shoot the light into a crystal and 2 different photons pop out at a 45-degree angle. That's not exactly a slit. You know, what are you talking about? You know, and that's the bullshit, right? There's just so much bullshit. And you're saying, why don't they as students say, well, I'm a little sick of you telling me shit that isn't true? You know, because I go investigate and I find out Eddington said in his own journal, you know, I got 10% of my data quality. Everything went wrong. I wouldn't stake my life on these results. And yet these people tell me this is a perfect experiment and they prove light is bent twice as much by gravity when, bullshit, they proved it.
Notice that water is a bent molecule. It's not straight. You might think H2O might look like this. It might look straight, but it actually isn't. It really is bent like this at a very specific angle. The reason it's bent like that is because I haven't drawn them in this or have this in this thing here, but there's extra electrons on the top that are not shown here that are pushing the 2 hydrogens down at an angle. So there's a lot of electrons around the oxygen. Some of them are pushing the rest of the molecule down. So what's really going on here is the oxygen is very, very good at attracting electrons. So what this is between the 2 molecules is the oxygen and the hydrogen, they're sharing electrons. That's what water molecule is. It's a sharing of electrons between this atom and this one. But here's the deal. They're not equally shared. That's the thing. Oxygen has more protons in the nucleus, and for other reasons that go beyond this lesson, not just the fact that there's more protons, but there are other reasons. Oxygen is just has a much stronger force pulling electrons in its direction. Hydrogen only has 1 proton. Remember?
So yeah, and so but it has these, you know, there's 2 gaps where these hydrogens can stick. So there's 2 missing electrons on the outer shell, and that's what the hydrogens are taking advantage of. They're just sticking their electrons into those missing locations, the places that's a little weak. And so there's plenty of red to point their blue thing at, you know, so to speak. But the fact is that if you know, theoretically, you could argue that it must be more about the missing electrons where they're missing, because theoretically it would still be better balanced if the other hydrogen was exactly on the opposite side. It's just that's not where the gaps are. The gaps are next to each other, not, you know, on opposite sides. And the gaps are in those positions because this is all very strict geometry. You know, you're building it, there's only 100 configurations of a nucleus. You know, there's only 100 ways you can arrange electrons and protons, and it's durable. And that's the problem, is that the interior structure is telling the electrons on the outside where they can be.
It's element number 1 on the periodic table. And so it's not able to suck electrons in and pull them in as much. So even though they're shared here between these two, they're not equally shared. They're pulled slightly more toward the oxygen than the hydrogen. So because they're pulled toward the oxygen, this part of the molecule, the oxygen side, has a very slightly negative charge compared to this. The hydrogen has more of an exposed
Yeah, right. It has a very exposed proton, so it's really wants to stick to almost anything. That's the whole point. The water wants to stick to stuff because it's got a bunch of proton, and all the other atoms have a bunch of electron on their surface. So obviously there's lots of places where the water molecule could find a place to attach. And that's why it's a good solvent, because it sticks to things really well.
positive nucleus, so it looks a little more positive. So I went into some detail there, but really all I want you to pull out of it is that water is bent. That's important. And secondly, it's polar. That means the oxygen molecule, if you had a charge meter, it would show that oxygen was slightly more negative and hydrogen in the molecule was slightly more positive. So it is an overall neutral molecule. If you look at it from far away, it's neutral. Okay, it's not an ion. It's just that within the molecule, this part of the molecule is more slightly negative than the hydrogens on the ends.
Okay, so they basically argue that all atoms, almost all the atoms, are polarized to some extent. So all of them are magnetic, but they're only magnetic as individual atoms. And as soon as you put them in a group, then they start pointing their magnetic fields in different directions. It all turns back into purple again. So that's the problem. But the atoms themselves all have some lack of symmetry.
Inside your microwave is an oscillating electric field. Remember I said it's an electromagnetic wave? Well, there's an electric field as part of that, so an oscillating electric field that is created in there, and it switches back and forth at 2.45 billions of times per second. This is gigahertz. This is the frequency of the waves. You know, light has a frequency. You can look it up in a chart. Microwaves in your microwave oven, 2.45 gigahertz. Basically, it was chosen to match the natural frequency of the water molecule, much like the swing set has a natural frequency of oscillation as well. Now, here is where the rubber meets the road. As the electric field in the waves that are shooting in switch back and forth at that rate that we just talked about, 2.4 billion cycles every second, it basically pushes and pulls on the chart.
Okay, so we know he wasn't selected again. So she already told us the story. It was accidentally found. It wasn't selected. Yeah, that's a good face too. Anyway, sorry. It wasn't my fault. Try to fix that.
Charged in.
There, that's all better. Anyway, so what was he saying? Oh yeah, the field. So it's not a field; it's photons, and so you're creating an object that's oscillating. Okay. And you're putting photons into it, and it's going to jiggle them back and forth. And the fact is that you're going to now release them, you know, with a whole bunch, then none, then a whole bunch, then none, then a whole bunch. So you're just releasing them like a radio antenna and spilling them into a box, and they're going to reflect and bounce around inside of the box. And so that frequency is going to be maintained, and it's going to just keep that line of force, you know, where there's a compression and then a relaxation, then a compression, then is going to keep hitting the surfaces. So obviously it's going to push, and then it's going to not push, and then push, and then not push, and then push, and then not push.
Of the water molecules, and it causes them to rotate back and forth, billions of times per second, basically like billions.
See, it can't create a pull. It can't be push-pull. It can only be push. And you can either have a hard push or a soft push, but I mean, it can only be push.
Of microscopic little compass needles switching back and forth. Okay, I'm using loose analogies here, but that's basically what's happening. And those water molecules are trying to rapidly align with this field that's switching back and forth 2.45 billion cycles per second. So you might remember our friend here. This part of the molecule is slightly negative, this part slightly positive. So as an electric field has a direction, it's a vector, it comes in here as a traveling wave, then it's going to push on one part of the molecule and pull on the other side. Remember, electric fields push on charged particles, right? That's what electric fields do. They push positive charges one way and they push the negative charges in the opposite way. That's what they are.
They push, yes. It's always a push, though. But whatever. So the fact is, it's just like little magnets. And so the little magnets are going to do this, and they're agitating the substance, and therefore it's going to get hot. But I think it goes deeper in the sense I think you're breaking the molecular bonds between the water molecules, so you're basically turning them into steam without using heat. You're using the microwaves to force them to do the state transition, and the state transition will automatically, as soon as they're turned into a gas, they will have more energy, more mobility.
Right? So by doing that, it might cause this molecule to rotate. But then when the molecule rotates, then the electric field has switched direction because the electromagnetic wave has an oscillating electric field and an oscillating magnetic field. So the fields are flipping back and forth 2.4.
Yeah, whatever. So there's no fields flipping back and forth. They're either you're either condensing or expanding. Compressing, expanding, compressing, expanding.
5 billion times per second, right? And so it might push the molecule this way, but then very, very quickly later, it flips it back the other way, it flips it back the other way, and this flips it back the other way. But here's the thing. This molecule has a natural frequency that it likes to rotate at, just like this pendulum does right here, right? Because the restorative force of gravity is what's doing it.
So you could argue it's just about the size and the pivot, and so the fact is it has to pivot on those two molecules. So that's almost like saying that's the length of the pendulum. So you have to have the wobbling force at the same speed that the pendulum can wobble. So the pendulum was a good example, at least in comparing it to the molecule having a size, and that arc is going to be its resonant frequency.
Here there's inertia in the molecule and the shape of it and all of that. And so if you try to push this thing and oscillate it like at 10 gigahertz, then it would push it a little bit, but it wouldn't be.
See, no matter how, if it has a length, it doesn't matter the condition of how much energy hits it, because if it's a little bit of energy, it'll take just the same amount of time as if it's a lot elastically. So it's always going to have the same period, no matter whether it's moving this little bit or it's moving this big arc, it's going to have the same period. So the same frequency is going to be able to stimulate it no matter what speed it's vibrating at.
Just like pushing the child on the swing set. But the 2.4 gigahertz frequency aligns perfectly with the natural rotation mode of this. So it's very, very good at getting them to move back and forth, back and forth, back and forth, back and forth, back and forth. And then your plate is spinning around in the field to catch the waves at all different angles because they're bouncing around and they're randomly oriented. The molecules in the food are randomly oriented. Some are like this, some are like this, some are like this. But the waves at some point are going to hit some molecule in a way to get them to oscillate. And that's going to rapidly...
Right, so they'll all be oscillating at different amounts. Some will vibrate a little, some will be vibrating a lot. But the period at which they vibrate will all be the same.
Agitate them and rapidly heat your food up. Now, this rotational mode of the molecule is what scientists actually call dipole rotation. See, it's a big fancy word, but it means the thing flips over and over like that. And it's the primary way your microwave heats your food. But there's actually more happening at the molecular.
Yeah, I would still argue the more happening is that it's just breaking all the bonds between the water molecules. The water molecules they're not a liquid anymore.
Level. I almost wasn't sure if I should go into this detail, but whatever, it'll take a second, so let's just talk about it. The water molecules also experience a slight stretching and bending of the hydrogen bonds. So I want you to imagine the molecule being repeatedly squeezed and then stretched along its...
Yeah, well, it really can't be squeezed and stretched unless it's connected to other water molecules. So that only happens in the beginning where it's bending each other. They're all feeling each other's motion. But once they break free, then they're going to oscillate at a much higher velocity. They're going to oscillate at a higher, the speed will be the same, but the speed will be different, but the period will be the same.
As the electric field fluctuates and rotates back and forth. And what I'm trying to say here is the primary heating method is rotating the thing back and forth like this, but also it might be stretching it back and forth like this, right? And so you're getting a little bit of heat from flexing and you're getting a little bit of heat from rotation. However...
Yeah, I don't think so, but whatever. This is all... Anybody can make up a theory about this kind of crap almost. Obviously, you have to have some understanding of the rules and the mechanics and all this kind of stuff, but I'm just saying there's lots of room for arguments about, again, the transition fact that you're changing it from a liquid to a gas is itself energy positive.
the rotational vibration is the dominant way that the water is heated in a microwave. Now, all of this molecular movement creates friction. I mentioned that before in the water molecules, and they bump into their neighbors, and it
Okay, so it's not really friction because it's, it's it's direct transfers from, in the small scale, you can't really call it friction because they're just transferring their energy. So it's all just transfers, and, technically friction, I don't know if that's the right word for what's happening on a molecular level. We call something friction because we're causing the momentum to exchange into the ground and we can't see it. We're going from something really big to something a billion times smaller. So we call that friction when we make that gigantic leap. But the molecules of water aren't making a giant leap. They're literally bowling balls banging into bowling balls.
Transforms the microwave energy into thermal energy, which is just the energy of motion, agitation of the molecule.
So again, thermal energy is the same thing. It's mass moving. So it's all momentum. There's nothing else in this universe happening. There's mass moving, a velocity, and that's it. There's nothing. That's all the action there is in the universe. Everything is just a transition of changing the momentum from something big that has motion to something small that has motion, and then taking something small like a photon that has motion and converting it into something big that has motion. And those are the only things happening, is the exchange of MV, mass and velocity. They combine. A photon hits, if it's absorbed, it means you actually are pushing an electron, and it'll keep happening until electron hits something, and then that bit will fly off, and so there's rules to it, but you're just transferring MVs always.
We call it heat. So it's kind of like having billions of molecular spinning tops, and all of them are bumping into each other and sharing their energy. Now, I can read your mind, and I know what some of you are thinking.
Oh, I don't think you could. Yet if you did, you'd be saying, why don't you just talk real? Why don't you have a real conversation about this physics instead of just preaching a story that you really haven't proven?
There, you're probably thinking, whoa, wait a minute, radiation? Are we making our food radioactive when we use a microwave? What is going on with this? Is this dangerous?
You don't want to end up with Alzheimer's and dementia later in life, so you should stop eating honey.
Yeah,
and I'm going to explain why.
Crap,
Hardly
bitch.
Anyone knows.
Yeah, you should stop.
And this is where I need to clear up a common misconception.
Seller.
It's not any.
Thinking you can fix all your ills with some kind of, just smear some hell honey on your forehead. It's just such a pile of crap. All these. It's disgusting, this commercials, all this fucking voodoo and snake oil they're letting people sell. Should be against the law. Anyway, so where are we? Let's see if the chatters have anything. Nope. I knew there was a point I wanted to make, and it has escaped me. I bet this guy thinks accelerating water into the atmosphere would simultaneously cause the mass to disappear and become infinitely heavy, creating a massive black hole. Yeah, exactly. It's just so, the physics is just so wooey. But yeah, they'll get into all this kinetic energy crap. So as soon as the real thing is that, yes, if you convert the energy into a small number of little things moving, they're going to be going very fast. And all of a sudden they'll calculate some preposterous amount of energy created. So it's a lot like the lever, right? I can take something very heavy, moving very slow, and I can create something very light, moving very fast, and they'll square that velocity. And so they'll claim I can make an insane amount of new kinetic energy by just taking a heavy, slow thing and converting it into a fast, light thing, and and come up with these insanely silly numbers. Billions of times more joules of energy because I made a little thing move fast. It's all so bad. All these, and again, these theories, they should be able to admit, Kip Thorne, working on that silly wave detecting machine, LIGO, just made up a theory, that you could turn mass into gravity. You know, he just made it up. It's just, there's no reason to believe you can convert electrons and protons into gravity. You know, bent space, that essentially. And the reason why they came up with the theory is because they know if they made real photons, you know, if if they converted the matter into photons even, there would be so much energy that you couldn't possibly, you know, the universe would get, everything get pushed away from wherever these events happened. So there'd be a huge pile of empty space all around these collision events between black holes. And they don't see anything like that, you know. And the energy would blow everything up. Everything would be getting burned up as it pushed out because it would be just too hot. So they avoid all that by turning it into gravity. You know, because gravity's safe. It doesn't hurt anything. It's just, it's all so silly.
I mean, it's good to ask the question, absolutely, but let's go ahead and answer it here. Not all radiation is created equal. We kind of treat radiation as a dirty word, you know, radiation. But, you know, all light hitting you from the sun is technically...
Right, so all those arguments should be negated by that simple word ionization. So it really just depends on breaking the bonds of the electrons from the surface. So you just don't want to knock electrons off of atoms because all kinds of things can happen when you do that in terms of the structure of the material. So, you know, but that's all that we're talking about is ionizing radiation. You don't want to break atoms off of the surface because then some other bad atom might stick where that other atom was, and it'll fuck up your genetic code and all this other shit. And again, the argument is what makes it ionizing is the fact that you're doing this, you know, you're hitting it very fast with the same amount of energy, and that's the difference. You throw all the energy in a short period of time, the rubber ball can't handle it, you know. So, you know, you hit a rubber ball with a bullet, the bullet goes straight through the rubber ball. So we can obviously disrupt the atomic structure, break through it, and so yes, if you have all the energy in one little tiny bit of space, it can bore holes in things. And if it's separated and over a period of time, it won't bore a hole. I mean, it's that simple.
Radiation. Radio waves that go through walls, radiation. We use that word, but not all of it's created equal. So there's a crucial difference between something called ionizing radiation. That would be higher frequency, higher energy radiation, like X-rays and gamma rays.
Right, but it can be low frequency in the sense that, you know, you could have a high energy electron. But it doesn't necessarily have to be pushed by a bunch of force. But the electron itself is going to be a big block of crap that, at moving a velocity, it's going to ionize atoms. It might ionize more than one. So it isn't just about photons. It's about any way that you force a bunch of energy to interact with something very fast, and you will break the defenses.
And then you have the non-ionizing radiation.
I mean, just like the point on an arrow defeats material objects, you're just using another kind of wedge, the wedge of speed. So you can have the wedge of a shape, and then you can have the wedge of speed.
Like microwaves and radio waves. Now here's where I need to bring a little bit of quantum theory into the discussion, right? So we know that light and all of this radiation comes in as a traveling wave of electric and magnetic.
Right, we know, you must believe. We know the Holy Ghost, you know, wears a dress on Sunday. Why? We don't know that, but, you know, we know he wears a dress.
Fields. But we also learned around the turn of the last century, around 1900, a few years around there, that that light also comes in packets or chunks. It's not like a water...
So this is just bullshit. Oh, we know it's this wavy, blah, 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 blah. And then we know it's a chunky, clumpy thing. I mean, it's, you know, it's one or the other. You can't have it both ways. You know, and so I go back to Feynman again because he's just, you know, playing the game a little bit, but he's just basically saying, look, it can't be the wave thing because our detectors collect chunks, clumps. But then the argument could be, well, that's because you just have clump detectors, you know, so of course that's all you collect is because you're just collecting the clumpy parts. But, I mean, the point is that it can't be both. So quit playing the game. Just say that you haven't collected enough evidence yet to draw a conclusion. I have, and the conclusion is it's clumps, like Feynman. It's the only sensible explanation.
In the ocean that stretches from horizon to horizon, it comes in actual packets, like little bullets of energy, and we call those photons, right? And we say
right. So but the photon isn't the bullet. The photon is the sequence of bullets. You have to hit the surface more than once to have a photon, because you're creating electricity. Electricity has a direction, that's always true. And electricity, we already know how it happens. It's got to push an electron into another electron. And it only works, just like sound, when you have enough velocity. So you can't make electricity travel through a wire unless you get the electrons going fast enough to push on each other aggressively enough to take one electron and change its position and force the other electron to force the other one to change its position and create that cascade. That's electricity. And you have to have enough momentum in the electrons to force them to do that. And so that's why you can only create the electricity with the ultraviolet light and you can't create it with the infrared. Is because you're not going to get the electrons moving fast enough, because you're not hitting them before they slow down. You have to hit them while they're still moving. You can't hit them when they stopped, because then you're just going to keep adding 30 miles an hour, so to speak. You need to add 30, and then you need to make 30 into 60, and then you may need to make 60 into 90. But photons don't hit. A whole photon is giant. The frequency itself is 500 atoms across at least, maybe 1,000. And so the polarization is just as gigantic. So there's not a single photon hitting a single electron. It's a piece of the photon hits an electron, and another piece hits another electron, another piece hits another electron. And it's a combination of their pressure against each other that you're hitting. You're pushing the water. All right, let's see what this comment is. Let's see. Both waves and particles. I think that's the way we are, right? Yeah, both waves and particles and clumps, LOL, and cottage cheese, yes. Of how the phenomenon, I don't know what that means. Okay, it's like they think that because the instruments that are used for measuring give wave outputs, but they really don't. So I'm just saying it's just a perverse interpretation. Again, if you take the two-slit experiment and you put waves coming out of the two slits, the center of those waves, that math won't work. So it's clearly not about waves going through the opening. It's just wrong. That math won't get you the right answer. All right, that the phenomenon itself must have a wave either than... Phenomena itself must be a wave rather than the wave being an effect of how the phenomenon is affecting the instrument itself. Well, I'm just saying it's only interpretation that calls it a wave. It's just a frequency. So again, they just keep turning anything that has a frequency into a wave. All right, and again, water is a medium, okay, where the little bits are stuck to each other. So we understand why they have friction with a surface, and then we understand why they bulge and do all this other stuff is because they're stuck to each other. But there's no evidence that photons are stuck to each other, that these bits in any way react with each other. So it's just such a made-up pile of crap. There's not that much of a similarity when you really look at the patterns. They're not the same at all. I mean, water is jiggling up and down. It's doing all kinds of things that photons aren't doing. The photons aren't turning on and off. Yes, it is. It's just, the fraud is that they haven't proven any of this, and they won't even listen to the defense attorney. And they certainly won't respond even when they hear the little squeaks that the defense attorney might be making from the hallway. They won't even respond to those arguments.
It's quantized. Quantized means it just comes in chunks, and that's where the word quantum mechanics actually comes from. And the bottom line is, if the individual photon has enough energy, then when it hits the matter, like your food or maybe your skin or something, if you're
that's such a, the joke of the whole thing is, yes, the quantum mechanics is named after the idea of quantum chunks. That's, and they've turned it into a completely wooey, wavical, nothing's real, there's no real distance, there's no real anything. I mean, it's just so ironic, how they've broken both the word quantum and the word mechanics, because they don't have any of either one.
then if it has
And again, it doesn't have more energy. Again, it's just about the frequency and the fact that if you want to tip something over, high frequencies are much better at it than low frequencies.
enough energy above a certain threshold, then it can what we call ionize there. And what that means is it can kick out electrons and it can disrupt the bonds.
So it's not so much kicking them out, right? All you have to do is, if you move them with enough velocity, you've got electricity. And then if you move them with even more velocity, then they'll fly out of the surface. So there's two phenomenon. There's the photoelectric effect where you're making electricity, and then there's the photoelectric effect where you're basically, deteriorating the substance. So electricity, electricity can travel through wires for 1 billion years without hurting the wire any, but you can't break off the electrons without destroying the substance. Eventually the substance will disappear because you're, deteriorating it, and ions are flying off, whole atoms are breaking off. So it's a kind of a big difference between the radiation that breaks atoms off the surface and the radiation that just causes electricity. And they ought to make that distinction a little clearer. They shouldn't call them both the photoelectric effect. They're not the same thing.
Between molecules. So you have your DNA, right? And your DNA is a long chain of lots and lots of atoms bonded together into a long chain, right? But in order to disrupt the bond of DNA and cause cancer in you, you have to have the individual photons with enough energy to actually break one of those bonds. You have to. If it doesn't have enough energy to break one of those bonds, then it's not going to do anything at all. It'll pass right through it, or it'll absorb as energy and vibrate, but it won't break a bond, right? And so for microwaves...
So I don't know if that's exactly the way... Cancer is a specific kind of breaking where you just start making more and more of the same cells. So it's a very particular break in a very particular location, I guess you'd have to argue. And the other kind of breakage doesn't make any difference somehow.
The photon energy just is not high enough to do...
I mean, it's kind of funny. I mean, they don't blame a bunch of other diseases, liver disease or this or that, on ionizing radiation, because somehow your body recovers from that problem. But it won't recover if you start, if you've got cellular, uncontrolled cellular production.
Basically, there's an equation in quantum mechanics. The energy of a photon is equal to h, which is Planck's constant, times f, the frequency. The higher the frequency...
So again, it really isn't anything called real energy. It just means its effectiveness at breaking atoms. So they should have a different word for this. It shouldn't be called energy. It should be called effectiveness. So you could say the effectiveness of an arrow is vastly improved if I put a point on it. I'm not making more energy. The arrow's not going to have more energy, but it's going to be a lot more effective. So maybe they should have like small e for effective. Okay, effectiveness versus calling it real energy, because it's sort of just cheating the truth. It's not real. It's not more elements moving. It's not more MV. It's just that you've made it more effective at breaking atoms by compressing the frequency. I mean, there is a real difference there. And, they don't pay any attention to that real difference.
Then the higher the energy of every single photon coming out. So when you get up into X-rays, that's a higher frequency than everything we've been talking about.
So you can sort of understand, if you have chaos, so I have a bunch of particles in all kinds of locations, and then I'm going to try to make it into a pattern, that I'm going to have to apply energy in some way or other to create the pattern. I am going to have to do this compression and expansion, but you can understand that where I'm compressing, I might be using energy, but where I'm creating the expansion, I'm gaining it. So, you know, it all adds up in the end as being, you know, energy neutral. I can't say that for sure, though. Yeah. So yeah, but it's. I'm just saying the truth is, if you just think of it as bowling balls, obviously if you can get the bowling balls to all be right behind each other, they're going to be more effective than if they're, you know, a mile away from each other. The pins will recover, so to speak, if I give them time to. I want to hit them while they're still wobbling.
Here, higher than visible light, they have a higher photon energy. And if you go higher than that, you get into Incredible Hulk territory with gamma rays. And each photon is much, much higher. That's why we had such problems making the Incredible Hulk, because...
Oh, so why does he have to talk about a cartoon? I mean, you know, obviously the whole Incredible Hulk thing had so many plot flaws in it. You know, it's such bad sci-fi. You know, just because, you know, your cells and your atoms can't change and then turn back to what they were before and all that crap. So it's just silly, and your clothes can't... Yeah, it's just silly. Silly on so many levels. Why would you change color? Anyway, let's see. Thanks for taking the time to speak up about this. The backlash from the cult of society can be isolating and career-ending. So much cognitive dissonance. Yeah, well, I guess that's the only good news. I don't have any career to risk. But yeah, it's still very disappointing that physicists just don't talk about how bad their physics is as science. It's just really a bad science. They really have jumped the evidence. They haven't done what scientists are supposed to be, is be disciplined and careful. And they haven't done any of the all the elemental experiments. They haven't crashed cars. They haven't done anything to tease out the truth. They you know, even the double slit experiment, you know, it's such a simple experiment, right? And they've never even taken photographic film and put it on this side and that side. So here's your two slits, you know, and what you want to do is see, well, do any of the photons go this way? Do any of them go this way? Do any of them ever hit those? Do any of them come out at those angles? And they've never even tested it. And it's so simple. You just put it all in a dark room, you let the photons shoot through the slit, and you see if you can pick up anything over here. I mean, it's decisively interesting information because, frankly, it'll prove it's not a wave. Because if there's no photons going at those high angles, you know it's not about anything waving.
We're using gamma rays and, you know, disrupt his DNA or something like that. So basically, if you get above a certain threshold, then the energy can ionize and disrupt the bonds in your DNA. But if it's below a threshold, then it won't. And that's why visible light doesn't cause us a problem. Microwaves don't cause a problem. They will heat the food up, but they won't break any bonds, right? Infrared radiation, radio waves, none of that stuff will ever break a bond in a chemical, in any molecule in your body, so you will never have a problem. But you want to know where the threshold actually is? The energy threshold to actually break a bond and disrupt your DNA is right around the photon energy of ultraviolet. So you have the rainbow, Roy G. Biv, and right beyond violet, you have ultraviolet. Ultraviolet gets just into the energy territory for every photon that if it slams into...
So again, the image was reversed. High frequency at the left, low frequency at the right. It's just, you know, very unintuitive. And again, this just has to do with the fact that electrons have a limited space. You know, all the different distances they are from the nucleus. You can understand there's only so many levels. And so they can only move a certain amount of distance at a certain amount of velocity. So as individual atoms, it's very hard for an electron to move fast enough, okay, to create ultraviolet or those higher radiations. Obviously the same force, okay, the atoms have to make the force that is going to break the other atom. So in a sense, you have to break an atom. That is, you have to shoot the electron out of the atom to have enough velocity to be able to create a photon of enough compression to break an atom in the other direction, right? So you can't really emit a force at a high frequency unless you're breaking atoms to do it. So you have to destroy atoms to create destroying radiation. You have to create ionizing. You have to be ionizing a surface to be creating radiation that will ionize a surface.
a DNA molecule at the right spot, it can break a bond. And anything above that also could break a bond. That's why we need sunscreen. That's why we have to be careful to get sunburned. It's not because of the visible light. It's because the invisible ultraviolet light has just enough energy to ionize some of the bonds in your body.
Right, and it's usually about some kind of mole or some other skin defect, some scar tissue or something else that's the most vulnerable, I guess, as I understand it anyway. But that's just skin cancer. It's not even getting into all the other kinds you can get. Yes, they are supposed to constantly be challenging their conclusions. What they're supposed to be doing is looking for the very weak arguments that they have and saying, okay, that's a weak argument. I need to shore that up. That's what I have to constantly do. See, I always have the pressure put on me, right? I'm always, everything, I can't even make a simple mistake of talking about a wrong decimal point without them picking on it. So I can't make any mistakes. And so everything I argue, I can't have a defect in the theory or the model because they'll capitalize all over it and jump all over it. But they don't allow me to do that to them. They evade hearing it, so they don't have to pay any attention. They just close their little ears and pretend their model doesn't have these huge defects, because they never have to answer the question, why hasn't the Eddington experiment been done from space? I mean, it's a 5-minute experiment, cost maybe $500. Why haven't we done it? We couldn't do it well enough from Earth. So why aren't we doing it with the 400 times better resolution from space? They won't answer the damn fucking question. It points to a very weak theory, okay, when you have an experiment that you haven't been able to successfully replicate beyond reasonable margins of error. It's just so corrupt.
I'll just say the difference is quite stark as well. So the photons that are running around your microwave oven, they literally only have 1/100,000th the amount of energy needed to break a bond in any bond in your body. 1/100,000th. So it's not a little bit different. It is many, many orders of magnitude too small to do anything. So when a microwave photon...
So I know, but it's too small to do ionization, but it is still, obviously the energy can disrupt the water molecules that are right on your surface, so they can start messing with you. But they're just not going to mess you by ionizing you. They're going to mess with you by burning you. Well, melting you, whatever the right term is. Creating steam inside of you.
Hits water or anything if you were to stand inside of a microwave. It wouldn't break the bonds of your DNA. What it would do is it would heat you up. So you would get damage from getting too hot. Just like if you put yourself in a regular oven, you would die because it would be too hot. But it wouldn't be because of cancer. So now I want to touch on the question that you probably are wondering, that I find fascinating. How does your microwave create these waves in the first place? How are they made? So in the heart of every microwave is a really fascinating device called a magnetron. And it's actually a remarkable piece of engineering. So I want you to...
So again, yeah, he's not really going to go into enough detail to make it worth even paying attention, but just because he's not really getting the whole cavity thing and how the material itself has to be causing the resonant frequency, the distance between the surfaces, and you're just really bouncing shit between the surfaces.
Imagine a metal cylinder, and inside of the cylinder has cavities which are carved onto the inside, and it's surrounded by really powerful magnets. When you apply a high voltage, what happens is that electrons are actually released, and they're forced to spiral around on the inside of these cavities, which...
So they didn't even do the electron part right? Because you have to have some kind of anode, cathode kind of thing where you're shooting this voltage, okay, and releasing it, into flux of some kind. But there's no description, and so obviously you would argue that has to deteriorate because you are, obviously creating a lot of vibration. All right, let's see. I know all too well myself, unfortunately, it's not just physics, they're corrupted either. Of course, it's not just this one subject. Well, I would argue that physics is so much dramatically more broken than, say, biology. But obviously they've created all these other psychology subjects and all kinds of other mushy science subjects where they can make up all kinds of crap. But generally speaking, chemistry is not nearly as fucked up as physics.
carved inside of this device, and they're doing it at really, really, really high speeds. And as they spiral around and around, they create these electromagnetic waves. I'll tell you more about how that happens in just a minute, which are
Yeah, they're not waves. Okay.
microwaves at exactly the correct frequency to heat the water. Now, there's an old saying when I used to study this stuff in great detail, and that was that microwave engineering is like black magic. And I don't mean the people that design microwaves. I mean anybody working with microwaves. You might be making an antenna to broadcast something across the country.
All this stuff is, in a sense, it's very, over time they've engineered it and engineered it and engineered it, taken all the inefficiencies out, and it's all gotten to be quite magical. I mean, a fucking cell phone is quite magical when you think of the fact of just the insane amount of processing being done so efficiently with so little electricity, all of that crap. I mean, it's just amazing.
Or satellites. Lots of satellites use microwave frequencies for communication, not for heating food. There's lots of frequencies in the microwave band, and we call it black magic. Let me just tell you just a second why. When you study circuits, you start by studying DC circuits, direct current. Nothing is oscillating, just a battery.
So that's the interesting part about microwaves too, is that the frequencies are so similar. So the frequency of the Wi-Fi is pretty close to the frequency of microwaves, and every time I use my microwave, I have a camera on a tablet, and it loses the signal because there's just enough leakage to interfere with the frequency of the signal and create enough noise that it can't resolve the camera anymore. Can't find it. Can't find the signal in all of the noise.
Straight circuit going back around. Everything is well behaved because nothing is flipping back and forth. Nothing is switching direction. But then you learn about AC, alternating current. And that's what comes out of your wall, right? And as the voltage and the current flip back and forth,
So it doesn't have to flip back and forth, back and forth. All it has to do is go on and off to do much of the same kind of thing in terms of create all kinds of chaos in the system because it's starting and stop. It's a jiggling crap. Jiggling is unsettling, just a fact.
back and forth at very low frequencies, then it behaves pretty well behaved because it's kind of close to a DC circuit. And when things are changing and oscillating very slowly, everything is very easily explained. As you increase the frequency, 10 hertz, 50 hertz, 1,000 hertz, you start getting up into the gigahertz. Eventually, you start getting into a frequency range where everything starts to radiate like an antenna. That's how we make radios. We set up a circuit and we cause electrons to go back and forth through the antenna very rapidly, and that creates a disturbance, kind of like throwing a pebble into a pond will create a disturbance that goes in all directions. So we're creating a disturbance by
So disturbance by disturbance, again, it's the speed of light, motion of electrons. You're just pushing on atoms. And as you push on the atoms, I could just do the simple analogy. The atom's like this, and when you push on it, it stretches. So the electrons pop out on the surface. So you're essentially, the pushing force is a compression force. And so it compresses the bottom first, and then it compresses the top last. And so again, that's the compression you're creating in space is not, it's moving like a wedge. It's not moving this way, it's moving this way. And when it hits the surface, it's going to cause the same motion in the wire because it's going to push at the bottom first and then push faster and faster going up. It's going to keep adding energy and creating the speed necessary to recreate electricity.
accelerating electrons back and forth through an antenna, and that creates a disturbance in the electromagnetic field. And as you get
So it creates a pattern in the field, and that's all it is. Just like this red, just like the blue, it's a pattern. I've changed, the signal, and now this is a different frequency, and only this frequency, and not the other frequencies. So I'm changing what it looks like, and that's all. The whole universe is, like I said, all objects are seeing, even though they don't have an eye. They're seeing the world. The world is hitting them, and they're projecting it. They're projecting back a reflection. Everything's at a thermodynamic equilibrium, so to speak. So it's all, you can't pretend anything truly absorbs the energy because it would just get hotter and hotter and hotter and hotter. So obviously it's re-radiating, and it's going to re-radiate it in some form that you're not seeing. So again, all the colors that this isn't, all the blue, all the other colors that got absorbed, well, they're going to get re-emitted, but they're going to be re-emitted as infrared. What goes in is coming back out. It's just a fact. Everything's just mostly reflecting the universe.
Closer and closer and closer to higher frequencies, every little thing in your circuit, every little, little strand of wire that wasn't connected maybe properly, something that wasn't on the circuit trace really perfectly, maybe the wrong length, everything starts to matter. The tiny gaps, when two pieces of metal come together, if there's a gap there, that tiny gap begins to look like a capacitor at very high frequencies. Everything starts to matter. So when you have things operating at really high frequencies, then again, the radiative aspect of everything's
Well, electricity has to keep going wherever there's a place to go. So it always goes from high pressure to low pressure. So, so there's lots of any place that's a little, there's a place to go, there's a place to go. It has to go to all those places before it can transmit any pressure. So it always has to fill the whole volume. All the atoms have to be pressurized. All the atoms have to be depressurized. So obviously there's a point where the volume can't be moved at the speed you're trying to move it. So you can't move that much water or that much volume at the speed you want to, because you have to make it move faster than the speed of light to do it. You can't empty the vessel and fill the vessel at the speed you're trying to. So we'll never be able to make, we won't be able to make frequencies that will create these kinds of radiation, because we'll never be able to pump that system because we can't move the volume.
no matter why. And so that's why we say microwave engineering is like black magic, because you have to have a lot of experience to know all of the different effects. Now I'm bringing this stuff up because to explain how a microwave makes microwave radiation, I can't do it all verbally. You have to draw a circuit on the board and stuff. But let me try to give you my best explanation of it. Basically, electromagnetic radiation occurs when you accelerate
Well, I suppose you could show us a schematic, and that might be helpful, but whatever.
electrons. Now, you can accelerate them back and forth through a long wire. That's what a regular antenna is, like on your CB radio or little antenna you see coming out of a phone or something like that. It's accelerating electrons up and down, back and forth through the antenna, and that causes a wave to radiate out that you can't see, but that carries information.
So, yeah, but see, that's not radiating actual photons, so that's the difference. The difference is that antenna is just vibrating, so to speak. The electrons are staying on the surface. To create microwaves, you have to actually eject electrons.
Resonant circuit in there accelerating those electrons up and down. Now,
You don't want to end up with Alzheimer's and dementia later in life,
you don't want to end
so
up
you
being
should stop eating
a crook
honey.
and a
I'm
shyster.
Now, another way you can accelerate electrons is to put them in a loop. You might remember from physics that whenever you take something and you spin it around in a circle like this, then it's actually undergoing acceleration, centripetal acceleration. There's an inward force from my fingers pulling.
All right, so obviously that's not true. So you can get it going, and if it wasn't for air resistance, it would just keep spinning and blah, 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 blah. So, whatever.
Around. And because it's changing direction, any change of direction is called an acceleration. Any change of velocity, I should say, is called an acceleration. And so,
Right, so you're not changing its velocity, so you're not accelerating.
if you accelerate electrons back and forth, then of course they're accelerating. And if you make them go in a circle, because they're changing direction all the time, they're also always accelerating.
So they're really not. So again, that's just wrong. Yeah, it's wrong. Something in orbit is not accelerating. Technically, frankly, it's not going any faster. Unless it's a parabolic orbit, unless it's uneven, then the velocity changes. But that's only because you're changing the arc of the orbit. So, gravity's providing all of the force to bend the path, so the object itself isn't accelerated.
That's why this magnetron is made in kind of a cylinder shape. And what basically happens is you have a very high frequency generator that's accelerating current back and forth through the cylindrical structure. And the cutouts that are in that magnetron, the kind of like the little cylinders that are cut out in there, they're making a resonant cavity at exactly the right frequency to only allow the...
So it's really not, I don't think that's true. See, this output coupling loop, whatever that is, okay, I think that's the thing that's really initiating the function. But whatever, it doesn't matter.
2.45 gigahertz oscillation to get strengthened and come out of the magnetron. So just like with the swing set, I have to push at the right frequency to make it resonate and to get energy in there. This cavity is constructed with the proper dimensions so that only the radiation of the right frequency can be amplified and resonated in that cavity from the from the driver that's there, and then it can blast out into your microwave oven. That's about as far as I want to go. It's a circular current combined with the physical shape of these cutouts to make the right frequencies pass through and go into your microwave. Now the microwaves bounce around inside the metal box of your microwave, and that's why the door actually has that metal mesh that you can kind of see in, but you can also see that there's a mesh there. That mesh actually keeps the microwaves inside because the distance in the hole.
So it doesn't keep them inside. It creates little holes that they, frankly, okay, the photons do come out, but they're broken. You've disrupted the polarization. They obviously have lost their polarization because you've taken hunks out of them. So if they were smaller polarized beams, then they could get out the holes, but they can't get out because they're too big a polarization, and so you've made a bunch of pieces. And but the fact is I can put a surface out there, and just like the fringe pattern created by slits, I can reconstruct a microwave. So you're still got microwaves going through the door in the sense you have pieces and they'll hit a surface and recreate their existence, so to speak. So I frankly think it'd be better if they just put a smaller window with holes and then had the rest of the, because you don't need the whole door to be holes. But there's plenty of shit flying out that would be better if you reflected it back in. Your microwave would be more efficient without the fucking holes in the door.
Of that mesh is too small for the 12 centimeter wavelength to actually pass through. It literally traps the microwaves inside.
So it doesn't trap them inside, it breaks them, so they're less effective. The ones that hit the door and reflect off the door are no longer effective as microwaves. They've lost part of their function. So you're degrading them. Each time they bounce off the door, they're getting degraded. So again, you'd be much better if they just made the window much smaller. You could still see in, yeah. You don't need a whole big window.
But lets the visible light out so we can see what's going in there. And inside the microwave, it creates patterns of high energy and low energy, and that's why your microwave has a turntable to help ensure that your food passes through the standing waves that are in there, preventing hot spots and cold spots. You know, it's kind of like, imagine going to the beach.
There's reflections that are really strong, and then there's reflections that are weaker. So there's places where it's strong and places where it's weaker because of the reflections being more. After it's bounced off 10 surfaces, the microwaves aren't as effective as the ones that only bounced off 2.
Very wide ocean, horizon to horizon in front of you, and you see a wave front coming. The wave is basically stretching from horizon to horizon.
Yeah, there's none of that happening here. Yeah.
Coming directly at you, right? Now you pick out of your pocket a soda straw, has a diameter of about 1 centimeter, and you put it on the ground right where the water is going to hit you, and that wave is going to hit that soda straw. What's going to happen? Is that gigantic wave going to pass through the straw? No. I mean, some of the water might get in there, but the wave...
Yeah, it's still going to have a frequency, so it's defeating your argument, okay? The straw is going to shoot the water in pulses. Just as the waves come in, it's going to be the same pulses going through the straw. So you're still going to have a frequency. And so that's not the point. The point isn't that the frequency got destroyed. The point is you broke the polarization. You broke part of the essential part of what makes the mechanism effective at disrupting the atoms. The whole giant big atoms. Let's see. Wow, that made total sense, and you don't need some dinky prop or cartoon. Yeah. Oops. Yeah, you made some oopses, huh? Yeah, oops happens.
The undulating structure of the wave, what we call a wave, is a periodic representation of a very extended...
Yeah, it's a periodic representation of a simple period between events. A photon is an event. There's periods between in its structure. It's a ... It's a mechanism. And it's clearly a mechanism. It's not just some blob. Photon hit the thing. No, that doesn't happen. It's constructed of elements. It's a composite object. It is not in and of itself a thing. It's a pattern.
Structure. That thing is never going to make it through a soda straw. Some water might lap into it, but it will not emerge from the other side as a wave front. In the
yes, it will. It'll be every single wave will create a little swoop through the straw. Whoops. So you still got the frequency. Bad analogy.
That it started. And that's what's happening on the door of the microwave. The 12 centimeter waves cannot get through, but the wave...
So again, he keeps saying they can't get through. Yeah, they can't get through as whole things, but pieces of them are going through the door. So you're losing energy through the holes. It's just a fact. It'd be better with less holes.
Length of the visible light from the light bulb in there is so small that it can get through. So it traps the radiation from the microwave on the inside, letting the visible light out. Now,
so again, it's not trapping it very effectively because part of it's going through the fucking holes. You're losing photons through the holes. It's happening.
I think it's pretty amazing when you think about it. Every time you heat up a leftover pizza, you're actually using electromagnetic waves to make water.
So, whatever, electromagnetic wave nonsense, you're bombarding it with little bullets, and at the right frequency, the little bullets will cause all kinds of motion in the pizza.
Actually dance or move around or agitate at the molecular level. You're actually harnessing the same type of energy that carries radio signals all the way through the air and through space and allows you to see this video just at a different frequency.
And again, they're doing the same thing. They're just reflecting energy. Okay, they're not creating it. They're reflecting it. Everything is just reflecting energy, okay? The absorption, just think of what absorption would mean. If I absorbed it, I'm going to get hotter and hotter and hotter. I can't keep it. I have to get rid of it again, or I'm going to get hotter and hotter and hotter. And fatter and fatter and fatter, frankly.
And the frequency that's chosen is very specifically crafted to be able to agitate the...
So more argument about how it was crafted when the guy's pocket melted. You know, his chocolate bar. He didn't craft anything.
Common molecule that we all, that we eat and drink and interact with all the time, and that's the water molecule. Now, these standing waves in the microwave, along with water content differences, molecular interactions, explain why some foods actually...
Yeah, and that's, it is interesting because, yes, it's better to have some minerals in the water, different things make the water, heat better, blah, blah, blah. It says all kind of interesting. I mean, if you heat distilled water, it boils at a much higher temperature.
Do heat quite unevenly, and why metal can actually spark in the microwave, reflecting the microwaves on the inside, and why...
So again, he calls that reflecting, when obviously to spark it's got to be absorbing and turning it into electricity. So it's collecting the energy and moving its electrons because of it, and that's the electricity you're making. So metal absorbs the microwaves, doesn't reflect them.
Coffee gets scalding hot while your plate underneath it doesn't get quite as hot. And I know it might sound a little weird, but the next time you're waiting for your food to heat up, I want you to really try to remember something. You're not just watching it spin around in the microwave. You're witnessing quantum physics, as cheesy as that.
So it's not anything quantum about it. It's all this wooey bullshit. There's no quantum part.
And electromagnetic theory in action, all miniaturized from the gigantic machine that was invented a long time ago to something that sits on your countertop. And it's something worth thinking about while you wait for your popcorn to pop. I'd like to thank you today hanging out with me. Please do drop me a line. Let me know what you think.
You don't want to know what I think. You won't interact. You're just What am I supposed to say? I mean, I'm supposed to say you're a charming person. Thank you for ignoring all counter arguments to the woo you preach. I mean, how do I even, characterize these kind of people? Because they're so arrogant and obnoxious. It's hard to be polite to the arrogant and the obnoxious.
The last thing you put in the microwave, and if it was tasty or not, and always remember to stay curious.
I mean, if you look at my videos, in the past, I tried very hard to be very nice to Jason, and he just, he still wouldn't have any part of it. He wouldn't respond in any way whatsoever. He doesn't want to hear what people think. He just wants to hear applause. Thank you so much. I wouldn't have known how to be an idiot until you taught me how to be an idiot. Yuck. People are just ass lickers. You're fighting off sleep, yes. Yeah, I'm fighting off nerves. So that's why I made a video. It's because I'm just... yeah, I got a microwave problem on the inside. Blood sugar or something, I guess. I don't know what exactly it is. I've always been an anxious kind of person where I have these little bouts of not feeling right. But it's just getting more regular with age, and I don't care for that. It's really quite unpleasant feeling. It's not like some kind of hard nausea or something, but it's just this, yeah. You just don't feel right. Quite irritating. That's why I'm quite sick of being alive. 'Cause I'm sick of feeling mediocre and worse. I don't seem to do much better than mediocre. And such. So I guess I'll hang around a little while, see if there's something else to... I did make a part of a video to the stupid blue moonshine. I mean, I can't believe, he made a 1-minute video. And why? I mean, who thinks this makes any sense at all? I mean, all these arguments about kinetic energy, all this stuff, even the relativity stuff, he can't argue or make an argument more extensive than a 1-minute fucking useless video where he just points out that dumbass Gary thought the decimal place should have been moved over one place. What an idiot. I mean, it's just, what the fuck? Picking on me over a decimal point? I mean, it's just so ridiculous. But yeah, there's no, it's like that. And then that, I can science that guy is just so fluffy and friendly, and everything has to be in this, poofy, fun language, and it's just so, brain stultifying. To live in this, vanilla world where you can't have a, you can't even call somebody a duty head. I remember as a kid we used to get grounded for saying fart. You really was a different world then, But yeah, it's... I guess I'm just way too tired of it and impatient to sit there and pretend to be somebody else who doesn't, who's afraid of words. And again, even if they want to call me some name, I don't, so what? Just you call me the name and then you make your argument. What's the big deal? I mean, why does the name calling have to be the only thing you do? Make your physics argument. And then I can choose to respond to the name calling, or I can choose to respond to the physics argument. But they won't make a fucking physics argument. So I don't have anything to respond to but this, stupid rhetoric that, somehow everything I'm talking about is wrong because I didn't think the decimal was in the right place. Obviously they won't argue the arguments, so they won't concede the simple thing like, oh yes, I also wish physics did more experiments so we could actually see it take 25 times the fuel to move something 5 times as fast. It'd be really great to have hard evidence demonstrating that actually happened somewhere on this universe. And that, yes, it's true that if we apply the right technology, we could make a ballistic pendulum that could actually collect more than just the momentum. So we could actually prove the existence of kinetic energy because we could actually collect more than just the momentum. The energy that's supposed to be able to do work, that's what kinetic energy is defined as, energy that does work. Well, why can't it ever do any work? Why can't it move a spaceship? Why can't it move a ballistic pendulum? Why can't it move a lever? Why can't it do any of this stuff? Why does it fail? Pulleys prove it doesn't work. So why can't they explain how I'm being deceived by the pulley? Because it really is conserving kinetic energy somehow. But yes, it all is quite horribly unfair. Let's see if I can put the chat. What was the chat called? I keep forgetting. I guess it's this thing. Yeah. So I thought, you know, it's an hour and a half later. I should be feeling better, but yeah, still feel pretty kind of pukey. Yeah, I mean, it does prove me right in so many ways, because the very fact that they keep evading my arguments, they keep not paying any attention to the actual arguments. I mean, I make them 5-minute videos, they still won't respond. They still won't actually, instead of misparaphrasing the argument, actually play the argument and then actually explain where I make the specific point, how the point isn't relevant. I mean, I could argue that you can, you know, prove that friction is variable because the thin ice argument proves it. I mean, it just absolutely proves that you can change how much you weigh per inch, you know, and slide across thin ice. It's proving you're making less contact with the ice, you're making less contact with the surface, you're applying less pressure to the surface. That's why you don't break the ice. So it's clear it's a time-dependent force. Velocity defeats the force. It's clear. Distance is irrelevant. Velocity solves the problem. Change the velocity, you change the outcome. But yeah, they won't ever hear that argument, then explain how that argument is a perversion or a misinterpretation of the reality. That it wasn't actually the velocity across the ice that saved you, it was something else. Well, point out the something else. Point out the alternative theory. That I changed how much I weighed by moving quickly across the ice. And the lack, like I said, the lack of evidence is so glaring. I could have some hope for humanity or these people as having some kind of integrity if they would at least admit that they too wish there was more evidence. The fact that they won't even join in and say, yes, let's ask some of these people to do more experiments, because we need more experiments. We need better experiments. I mean, the only collision experiments we have are like Bruce Yearney's wooden blocks on rubber bands. Is that all we're going to get? We're never going to get anything better than that? And then we have the Mythbusters who weren't even doing a kinetic energy experiment, right? They were just doing, well, let's crash cars because it's fun and it's good for ratings. So they weren't even doing a scientific test, but they ended up doing a scientific test. But that's all we got is accidental science. It's not even trying science. So let me see what how come there's so many windows open here? Yeah, I shouldn't have that many open. Let's see. Well, I don't need that. And what's this one? That's the one I need. Okay. So there's only 6 people in here. Okay, not great. But whatever. Thank you for the ones that are here, I guess. Something is better than nothing. Well, I don't want to call you a something that's just better than nothing. That's sort of an insult. But yeah, so the fact is, yeah, we need to get a physicist to answer questions. Somebody who's willing to defend their physics. And we can't find one. Can't find one who isn't a snowflake, a teardrop, a quiche burger, a ballroom dancer. Yeah, we need a real manly physics. Ooh, cat. Walking down the sidewalk. Feel so bad for the poor critters. Such a tough life. Here I am complaining, and they got it a lot worse than I do. The willful ignorance of the people has been the most disparaging thing for me. Depressing, I would say, or disparaging. Yeah, well, anyway. I pray for a meteor daily. Yeah, well, I wish praying worked, but yeah, likewise, you know, a nice instantaneous type death would be quite useful. But I have to finish my project. Yeah, I have to be proven right first, you know. Yeah, that'd be better. Like the day after I'm proven right, then the meteor hits. Don't mind typos, really. I'm not, you know, the grammar police. I can't type at all, frankly. My typing's getting worse and worse, so I mostly try to use speech to text, you know, some kind of, and then you always have to make sure it got the right words, you know, so sometimes I'll have the wrong, you know, R versus or, you know, that kind of crap. But yes, typing is, I was born just a little too long ago for men doing typing. You know, nobody, there was just like the typing classes in high school, there would be like 2 guys per every 30 girls, you know, in the typing class. It was just not something guys did. Well, I wish there were people seeing through the veil. Frankly, I mean, people are still pooping out babies and playing all these silly games, and it's all quite disgusting, frankly. And people are so dumb. I mean, the common average person is so fucking ignorant. You know, they've spent their life playing video games, doing all, you know, so they know how to pick a good character in a video game and get plenty of swords and weapons, but you know, but they don't know anything about reality. You know, they don't have any clue how a car works or any, you know, they're just so fucking ignorant. I was always, you know, as a kid, my sisters could change a tire. They could do shit, you know. They weren't complete, you know, morons. And people now they don't even drive now, for fuck's sake. I don't even know how people exist that way without a driver's license. But anyway, just really strange world. But yeah, those dumbasses aren't going to be able to change anything. They're not smart enough. And then there's all the conspiracy theories. I mean, all these people, you know, who actually believe, oh, they've been hiding the smear honey on your butthole theory, you know, to fix your pancreas or something, or your prostate, you know. all these preposterous pink salt shit, all this crap. And there's people falling for this shit. There's some guy selling glasses, and he's like, you know, oh, the corporations, why haven't the corporations outlawed this? It's so brilliant. They outlaw glasses? You know, you're just saying, yeah, I can't really see that happening. You know, Congress passing the you can't sell glasses law. Oh, well, that seems like a typo right there. I know, blah. I ultimately blame this one people for allowing it. This one people. They do psychop and brainwash the shit out of us, though. Yeah, well, I don't buy into any of that brainwash psycho crapola. There's no conspiracies. There really aren't. Nobody's smart enough to have a conspiracy. LOL, I was correcting. Yes, well, you were, whatever. But yes, I think I get your drift. But anyway, yeah, I was never a conspiracy person. And see, on my birthday, Kennedy was assassinated. So I always got, on my birthday, a big pile of Kennedy information. And the magic bullet theories and all this, so it had to be another assassin and all this crap. And you can look at that Zapruder film, and it's just so gruesome. And it's just like, there's no room for these other theories. I mean, it's just so obvious it's a high caliber fucking bullet. I mean, it blew his brains all over the car. It's just idiotic to say, some guy hiding behind a bush did it. Yeah, no chance, fuckheads. But that was another example where, it just didn't matter what the science said. There was just so many people that wanted a conspiracy. They wanted a bigger story than just some wacko, who... it's hard to even figure out why he chose... why Kennedy? It was just... Because he was playing both sides. He was basically a double agent. He made lots of trips to... Oswald made lots of trips to Russia. He was like always switching sides. And it's just funny that in one of his mood swings, he decides to take out a president. But yeah, the story just doesn't need a conspiracy theory. It's the perfectly standard motherfucker who, wants to... He can't change the world by distributing pamphlets. That's what he did, like me. He was a pamphlet distributor. Trying to get people to care and to get interested and blah, 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 blah. And he couldn't get it done. And so he was getting older and getting tired of it. And he basically decided, I'm going to be a hero in some other way. I'm going to, take out a president and I'll be famous. And so it was really good that Ruby shot him, because he was enjoying it, frankly. When Ruby shot him, Oswald basically had a smile on his face. He was being important. The FBI is taking him places. He's doing stuff. He was happy, And so, thank goodness Ruby didn't have anything to live for because he was dying anyway. And so he decided, what the fuck, I'll take that fucker out. Anyway. But yeah, you don't need a conspiracy theory. There's plenty of evidence, and it all, like I said, it's, high caliber bullet. The fact that a high caliber bullet would go through his neck and then go through Colony's shoulder and then go through his kneecap makes perfectly good sense. You'd almost say that the bullet that blew his brains all over the place probably had to end up somewhere besides in his brain. It really was an elephant gun, for fuck's sake. I don't know how big the bullet... the bullet must have been a 4-inch bullet or something. It had to be a hell of a bullet. There's so many things that just turn on all that. Look, Trump almost got... the guy almost was successful. It's just so funny, that little margin of error. And the very fact that Oswald pulled that off, though, those 3 shots, well, the first one missed, that's the fact. The fact is he missed in the first shot. And, the second shot went through Kennedy's neck, and then the third shot, was the payoff. But, it was amazing that he was able to pull that off. And it really is the way to go. If you have to go, that's, Kennedy got off lucky. He didn't have to get Alzheimer's and spend, like Reagan, spend 10 years dying. They kept Jimmy Carter alive for an awful long time, too. It's just, in a way, I just don't get why people think, wow, that's what I want happen to me. I want to be, a corpse that you keep alive. Gruesome. That's horrible. My grandmother lived to 107, and 3 days before she died, they strapped her down against her will to do an MRI. And it's like, why would you do a diagnostic test on somebody who's 107 fucking years old? I mean, it was just so, so fucking cruel. Yeah, well, I can't remember exactly when Ruby died, but, he died pretty shortly after the event, so, I mean, he was a real, flag waver, and a big Kennedy fan, obviously. So it was a very big blow to him. It was gruesome. The whole thing, all of it was just gruesome. It all happened when I was 4 years old. So, yeah, it did kind of fuck my birthday for a few years, because the anniversary of the assassination was, something everybody paid attention to. And so you didn't have your birthday on your birthday. Oh, let's not do this male circumcision, but I'll do it anyway. Look, I'm circumcised, and I don't see a problem, frankly. And I appreciate that they did me the favor. Frankly, because I don't see any advantages. So you can say that there's some advantage to being uncircumcised, but I would say that from my perspective, as I understand it, your foreskin ends up just gets stuck in the vagina, and you end up just fucking your foreskin. So to me, that doesn't sound all that appealing. But yeah, I can't live both ways, right? You can't do it. Nobody can really do it both ways, because the only time people get circumcised later in life is because something goes wrong, and it's some kind of defect, and obviously you can't get uncircumcised. So I mean, I'm just saying, it's just there's no way to resolve it besides just making these simple statements, and I could just make this simple statement that clearly it is better disease protection to be circumcised, and I think obviously it's a little more sanitary. Just obviously, I mean, if we had foreskin on our hands, our hands are going to tend to sweat and get smelly, and what's the use in that? So from my perspective, I can say I don't see any. I don't think I've sacrificed anything to be circumcised. So it's never been about a religion, but you have to understand some of the parts, especially the Jewish religion, the Torah, is a bunch of stuff about eating pork and washing your hands or washing your feet. I mean, it's all these rules about how to live, without getting plague and getting a disease. So a lot of it is just stuff they learned over time as being better, in terms of outcomes. You live longer, you live better. It's life advice, So it's not so much that it's about some religious edict. God didn't say do it. Why would God say get circumcised, right? Does that make any sense? Thou shalt have your foreskin chewed off by a rabbi. Obviously God wouldn't say that, because he'd say you're already built correctly. You don't need to be circumcised. So obviously it's something men figured out that it's a good idea to do. You're doing your kid a favor. Well, I'm just saying the number of messed up circumcisions are lower than the number of people whose foreskins cause negative effects in terms of sexual dysfunction. So, that point works both ways. But I'm just saying, there really isn't any excuse for a doctor to fuck it up. It's not brain surgery. I didn't read the comments on the most recent Blue Moonshine video because it's a useless 1-minute video that doesn't mean anything. And again, why is he dragging up this other subject? I mean, I'm making a draft physics channel. I made a channel for the very purpose of keeping the two subjects separate. So, I mean, shall I make comments on his video about ballroom dancing because he's interested in ballroom dancing? I mean, that would be a waste of my channel, wouldn't it? Wouldn't that be kind of insulting my viewers to sit there and change the subject? So, you know, if it's his choice, he wants to talk about that shit, that's his business. He wants to keep doxing me, that's his business, okay? I'm not going to play his videos then. You know, I'll paraphrase them, but I won't play them. I mean, if he can't be reasonably civilized, then just fuck him. But, I mean, just the fact that he would waste everybody's time with a 1-minute video saying nothing. I don't like Gary. Gary is a duty head. Gary doesn't know where decimals should be. Gary's poopy. What the fuck's the point of that shit? I mean, it's so fucking useless. Like I said, I made like a 6-minute response video where I'm saying, well, what am I responding to? There's nothing to respond to. So I said, well, unless he makes some other video or does something, I guess I'll just throw it in the garbage, because what's the point? There's nothing to argue. I made a mistake. Oh, well, tragedy. Yeah, I looked at 0.9 and said that didn't, I mean 0.09 and said that didn't look right. Well, what's the big deal? I mean, it's just a ridiculous nitpick. It's a ridiculous, trivial pile of nonsense. Oh, he doesn't know what a centimeter is, and he doesn't know what a decameter is, and he doesn't know what a meter is, and blah, 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 blah. This is such a pile of horse shit. But yes, calling me a nihilist is just so ridiculous. I mean, Jesus Christ. I'm constantly ragging about, you know, the value equation. You know, how could there be a value equation if I was a nihilist? Just points out that these people just can't be fair. They just don't have it in them. That's not how they were raised. It's not how they grew up. I mean, I just never grew up as thinking I would ever scheme or cheat. Cheating and scheming were, you don't do that shit. You know, those are black hatters. Those aren't John Wayne. You know, you don't, I mean, anything I ever saw that indicated what was good in the world, I didn't want to be a shithead. I didn't want to be a pain in the ass. I didn't want to be a breaker of things. I wanted to be a fixer of things. Let's see, what's supposed to be the point of peer review? Fix mistakes, not berate you personally, red flag for sure. Well, I mean, peer review in this context is, you know, impossible, because if you're going to get peer reviewed by somebody who believes it's a wave and you're arguing for particles, you know, that's not a peer, you know. So it's like saying, let's review the Jewish faith from the Catholic perspective. Is that fair? Or let's review Catholicism from the Jewish perspective. There's no peer review. There should be like people who are agnostic in their science, in the sense that they know what the evidence is. They know, and that's it. They don't know, they don't play with any of the conclusions drawn, they just play with the experiments themselves. And so they just wait for somebody to file a paper where they've misdescribed the experiments, and then they can critique it. But, you know, these silly conclusions that people draw are just that, silly conclusions, silly interpretations of the evidence. I mean, criticism is part of the necessary, skepticism, finding the flaws. And that's all everything should just be about. It should be finding flaws on both sides. Finding flaws in their description of their description of what evidence there is, and then their description of what the evidence actually shows. And there's just nobody doing that. And the only people that can do it are, frankly, the advocates themselves. This is, like I said, this is a trial. And you need the advocates to show the evidence in the right light, and so they show the other guy's argument and show how it has holes in it. And then this guy, and you find out who has real integrity in what they're saying. And I'm saying if you do that, you can see that they have no integrity because they won't even say the words that there should be more experiments. The very fact that they don't all say, yes, Gary's a shithead, Gary's an awful person, but he's right, we need better evidence. Let's all agree to push for that. Let's do that as a group and say, we, the people who are concerned about science and keeping it accurate and having integrity, let's all defend the premise that there needs to be more experiments. And they won't even say those words. And there's so many simple experiments. Again, the simple, where's my scale? The simple scale experiment. Just turn the scale sideways and see what kind of velocities produce what kind of weight. Again, the very fact that the stupid I can science that guy is arguing it takes 4 springs to move something twice as fast. I mean, who has any experience with that being true? It's just so ridiculous. There's only a tiny margin, right? I mean, it's hard to get twice the velocity out of a spring because the spring is going twice as fast. It leaves a big hunk of energy left in the spring. But you know that if you take 3 springs, you're going to have more than twice the velocity. I mean, how can he get away with saying it takes 4 times the energy to go twice as fast when it absolutely doesn't happen? Yeah, well, that's what I'm just saying. They're really not interested in the science. I'm interested in getting the truth. So if you can show me I'm wrong, okay, you showed me I'm wrong. But that's what I need to see it. I need to see credible evidence, and you have to make it complete in the sense that obviously, if you're going to say it takes 4 times the energy to go twice as fast, and your theory actually says it takes 9 times the energy to go 3 times as fast, I have every right to see that better experiment. That more dramatic one, because that's going to be a lot more convincing than the one you can fudge. But again, it's all provably wrong. I mean, obviously Niagara Falls builds gigantic turbines, that don't move, 60 hertz, 70 hertz, 80 hertz, who knows. But it's not a tremendous velocity. Why would they do that if the faster they can make the turbine spin, the more electricity they could produce? Well, the lever argument to me is just so good too. I mean, just the very idea that they're arguing for this silly 1.4 thing. I put the 2 mass going 1v in here, and I only get a 1 mass going 1.4 on the other side. It's just a ridiculous claim. But that's what the stupid I can science that guy was saying. It's basically saying that 3 springs only make 1.7 the velocity. 2 springs only 1.4. 3 springs only 1.7. That's even what the stupid AI says. The guy posted a whole bunch of AI stuff, so I went and looked at it. And the AI is basically saying 2 springs only makes 0.4 more velocity, and then 3 springs only makes 0.7 more velocity. It's just a ridiculous theory. It doesn't happen anywhere in reality. And they should account for that they don't have any experimental evidence showing that to be true. None, zero, nothing. Really is annoying and such. So, almost time to give up. And such. Let's see. Well, AI is programmed by programmers. So it's really not programmed. The program is just an algorithm. And yeah, the trick is that the only part programmed, that is organized, is the fact that they know the difference between people that have an education and people that don't. So yeah, they don't go read all the conspiracy websites. They read the scientific papers and the stuff that's, people wrote books. So they have a standard of popularity, pop culture. And it's basically comes down to Wikipedia. It's just really, some sort of Ask Wikipedia engine in that sense. That it's all groupthink. So you're just really asking, what does whatever we call a conventional authority say on the subject? And it's just a combination of the arguments made between the authorities. And so it really doesn't have any capacity to understand any of the subjects. It's just completing sentences based on what the average professional says is the facts. That kind of thing. Just paraphrasing the speeches of 50 presidents and just making a speech that's just a bunch of gibberish about how we're all, striving to reach for stars or something, and crystal cities on a hill, and it's just putting together a bunch of crap spewed by crappyists. But it can't think. It can't think. It can't understand the concepts. That's why it's not going to solve any problem until you make the problem obvious to it, and give it like solving a chess strategy or something. Something it can analyze to pieces, but it's only going to analyze it by model, running through the model and over again. It'll be, the simple thing it should be able to do, right, if it could think, was you give it the task of saying, what's the simplest way you can create a mechanism that creates repulsion between electrons and electrons, repulsion between protons and protons, but attraction between electrons and protons? Because I already came up with that mechanism, right? The simple mechanism is, well, if you have two electrons and protons, you just have electron force and proton force. And then you just have the circumstance that when an electron force hits a proton, it turns into proton force. And when proton force hits an electron, it turns into electron force. And it works perfectly. So it's dirt simple. But could AI figure it out? Well, so far it hasn't figured it out. Yeah, well, that's what I'm demonstrating. Every time I ask Google one of these questions, it doesn't give me the right answer. It gives me bullshit. It assumes kinetic energy is real, so it makes up the same nonsense and says, it's 5 million joules of energy, when no, it's only 50. It's a three-dimensional model of the Pushiverse in development. No, but the two-dimensional model, the guy should be working on it this month. So that will be good news. And so the little flaws will be fixed. And that should mean it'll work much better. and so then I'll be shoving it in your face a lot more. The three-dimensional model is, I'm just saying it's an awful lot of in 2 dimensions, 10,000 little bits moving is a lot. So in 3-dimensional, it won't be able to work in real time. So in 3 dimensions, the only way it's going to be able to work is you have to, let the program run for a half an hour and then get 2 minutes of video out of it. Something like that. Which is okay with me, but I'm just saying it's going to require some, it's a lot more complicated programming, that's all. Well, it's funny if it's getting questions that simple wrong about who won a Super Bowl, but it just points out that it's not. It can't fact check anything. It can't. It just measures it against the conventional, the most popular theory. That's all it does. It just measures it against the most popular sentence on the subject. It's a brilliant tool. I mean, I'm not saying it's not useful for anything, because there's lots of things like a cake recipe, where, maybe the AI could be a little bit better at, refining 15 different recipes into one recipe that does all the things you need that are necessary. That's probably not a good example, but, I mean, just the programming stuff alone is useful, And the fact that it can, give you code that'll actually work. So that's save people a lot of time. But, I mean, all this, it's not gonna do very much engineering, until they make it a specialist in the field. And still then, I don't think it's not going to figure out the Roman arch or something. It's not going to invent anything. I don't think there'll be any time where the AI is going to win a patent. I don't think it's going to happen. Unless you give it, like I said, you really have to give it the specific task and give it specific knowledge of the specific well, even then, like I said, all it can do is do permutation, so it can just find the right answer by accident because it tried every answer. So that's what it's good at. It can spend, it can do a million processes and try every way to create a notch on the key, and then put the key in the lock and turn it, and then put the key in the lock and turn it. It can do that over and over again, and then accidentally find the right notches on the key. It can pick locks through trial and error, but that's it. It's not going to be able to engineer it. It's just going to be able to discover it through trial and error. I mean, to make a thinking machine, I think they have to make it able to rewrite its own code. Because that's what we're doing all the time, is we're rewriting our programming constantly. We're changing it constantly. And that's what the AI needs to do. It needs to have a mechanism where the feedback loop is inside of it, and one set of programs is reprogramming the other program, and this program is reprogramming that program. And so it has that feedback loop. Yeah, well, I mean, obviously Islam is the religion of super moron. So I'm just saying, look, the world is getting dumb because only dumb people are breeding, and they're raising their kids with dumb ideas and dumb notions, and, fat and dumb. The world's just going to get fatter and dumber. I mean, I don't think Islam, there's only like what? The idea that you're not supposed to be a drunk is a good idea. You shouldn't be doing drugs. That's probably a good idea. So, I mean, Islam has something good to say about something, but yeah, what else does it have going for it? I mean, it's chauvinistic nonsense. You know, they really think they're going to make a better future if you grow a beard. Oh, everything will be just fine if we all grow beards. Yeah. What? Yeah, fuck that. It's not much of a statement to make to the world. Grow a beard. And, beat your wife. Well, look, the whole, right on its face, it's so stupid, right? I mean, the bombers of the Twin Towers were doing it so they get 50 virgins when they die. What kind of bribery is that? I mean, where are the virgins coming from? Who are these girls I'm getting for free to rape? That's something that's supposed to encourage me? I'm supposed to feel good that, oh, Allah's going to give me a whole bunch of virgins to fuck. What the why do I want virgins in the first place? I mean, what's the advantage? I don't see it, frankly. So, and then second, who are they? Where do they come from? You're just going to make synthetic virgins for me to fuck? And they're stuck? They don't have to like me. They don't have to, I just get them. They're my possessions. I can tell them what they're going to like or what they're going to dislike. I mean, it's ridiculous. I mean, it's just a sex slave. Oh, I'm going to give you a bunch of sex slaves. I mean, that's a pretty debaucherous bribe. I mean, it kind of shows that if you have a wife now, you must not love her very much. Because what's her purpose going to be? She'll cook dinner for the virgins? I mean, it's just such a moronic religion. But Christianity has those little elements in it, right? That Old Testament story about you can rape a woman, and it's not a crime if you marry her. Yeah, so tough shit if she don't like you, But if you can manage to rape her, then you can keep her as a wife. Oh, that's a real good deal. I mean, these primitive ideologies, where men made women property, it's just disgusting that we would cling to any of that crap. I mean, it's embarrassingly stupid. I mean, it's like you have to not have a mother to think that you would want to be part of a system that basically says your mother should be a slave. Your sisters should be sold as property. How the fuck could these be human beings? How could they think that way? Well, Buddhism is just ridiculous. Life sucks. Life is suffering. Life sucks. Life is garbage. Life is a fucking plague. Life is a disease. Yeah, go ahead, make more of it. What do I have to do with it? I don't have anything to do with it. Jump in a fire. Everything's okay. You escaped. You won't have to come back as a frog if you jump in a fire. I mean, just the very idea of, oh, I'm going to escape, but I'll leave everybody else to suffer and die. I mean, just that very idea is just so cruel and stupid. Oh, I'll take the escape hatch, and, I'll jump ship and get in the lifeboat and fuck everybody else. I mean, that's not a very ethical religion either. And it really is a religion. I mean, people want to pretend it's not a religion. I mean, the whole thing is based on some fable about how little rich boy Buddha, who had a very corrupt, money-grubbing father, realized that, oh, it's just so terrible, all the poor people suffering, how disgraceful, and then death challenged him by offering him the very kind of corruptions. What if I offer you a bunch of whores to fuck, and I offer you riches and rubies and diamonds? And Buddha wouldn't, sell out, for he wanted the truth. And so he finally got death to tell him what the great answer was. And the great answer was, well, if you want to escape and not be a poor shit eating maggots, jump in a fire. Yeah, that was the great ending to the great story. It's just a pathetically silly. They're all just such bad stories, really. I mean, the other one is, you're facing this stupid war that's going to massacre, half your people and half the other guy's people, and it's going to be just a horrible bloodbath. And, you're the general. And, well, you just have to do your job. Go ahead, kill them, because, there's nothing you can do about it. Because, see, it's determinist, it's the world, this is the way it is. You have to play your role. If you're not there, then it's going to be worse. If you don't help, engineer the slaughtering, it's a stupid rationalization for just the silliness of our existence. Life is ludicrous. That's the religion. That's what the religion should just say. It's ludicrous. It's ludicrously sloppy, inefficient. Deserve doesn't have anything to do with it. Fuck the whole thing. It's a silly game to play. Well, it's a ludicrous game to play. Well, it's just, I could relate some personal stuff, but I guess I won't bother. It was just, people and their grandchildren and all that. Oh, it's just disgusting. This creating babies and seeing it as some sort of great adventure. It's going to be, no, it's not going to be a great adventure. Tragic, stupid waste. Alright, so I guess I'll go. And such. And so forth and whatnot. So, thanks for the participation, as limited as it is. But, something. And, whatnot. And so forth and such and whatever. Till the next time. That's all there is. I can only do my job. I think I'm doing it with some dignity and fairly and ethically, and I can't force the world to be to give me what I deserve.